This is the story of the most terrifying object in the known universe, and it is not technically a black hole. TON 618 sits roughly 10.5 billion light-years away from where you are sitting right now, and it is doing something so violent, so relentlessly energetic, that even the word massive barely begins to cover it. Before we dive in, if mind-bending cosmic rabbit holes are your thing, hit the like and subscribe button. It takes 2 seconds, but it is what keeps this channel alive and the content coming. Now settle in, because things are about to get very interesting. There is an observatory in the hills outside Puebla, Mexico, sitting at about 2,200 meters above sea level on the slopes of a dormant volcano. The Tonantzintla Observatory, named for the town below it, spent decades cataloging the sky with quiet, methodical precision. Astronomers there photographed stars, measured their colors, logged their positions, and built one of the most comprehensive early surveys of the southern and equatorial sky that the mid-20th century produced. It was painstaking, largely unglamorous work, the kind of science built on thousands of nights of exposure plates and squinting at photographs under magnifying glasses rather than dramatic discoveries announced to a breathless world. In 1957, buried somewhere in that catalogue, entry number 618 appeared. The Tonantzintla catalogue listed it alongside hundreds of similar objects. It looked, for all the world, like a faint blue star. It was listed that way, tagged that way, filed and mostly forgotten, the way obscure catalogue entries always are, waiting in the dark for someone to look more carefully. That closer look did not come for another 13 years. In 1970, astronomer Margaret Burbidge and her colleagues turned better instruments toward that patch of sky and did something the original cataloguers had not done. They took its spectrum, breaking the light coming from that pinpoint source into its constituent wavelengths, the way a prism splits sunlight into a rainbow. What they found did not match a star. It did not match anything particularly close. The spectral lines, those fingerprints of atomic chemistry that tell you what something is made of and how fast it is moving, were shifted so dramatically toward the red end of the spectrum that the object had to be moving away from us at an enormous fraction of the speed of light. Not because it was zooming through space like a comet, not because something had flung it outward from our galaxy, but because space itself, the fabric of the universe between us and this thing, was expanding, carrying the light from that source and stretching it, pulling its wavelengths longer and longer over billions of years of travel before they finally arrived at Burbidge's telescope. That redshift, measured at z equals 2.219 by modern instruments, places TON 618 approximately 10.4 billion light-years from Earth. The light hitting our telescopes today left its source when the universe was roughly 3.3 billion years old, which means we are not looking at TON 618 as it exists today. We are looking at a snapshot of what it was doing in the deep, burning past of cosmic history, when the universe was young, dense, and ferociously active in ways it no longer is. The object logged in a Mexican observatory catalogue in 1957 turned out not to be a star at all, but a window into a time that no longer exists. What they had found was a quasar. The word quasar is a contraction of quasi-stellar radio source, and the name tells you everything about the confusion these objects caused when astronomers first encountered them in the early 1960s. They looked like stars through optical telescopes, tiny, point-like sources of light with no visible structure. But they were producing radio waves with an intensity that no ordinary star could explain. And then, as the spectral analysis revealed, their redshifts were enormous, placing them at distances that were, at the time, almost incomprehensible. The debate over what quasars actually were ran hot for years. Some astronomers refused to accept the cosmological interpretation of their redshifts, arguing that perhaps these were nearby objects that had been violently ejected from our galaxy, that some local mechanism was stretching their light in ways that mimicked cosmological distance. That debate essentially ended as more evidence accumulated, as quasars were found in sufficient numbers that the statistical arguments became overwhelming, and as the underlying physics came together into a coherent model. What a quasar is, at its heart, is a supermassive black hole in the process of actively consuming enormous quantities of matter. And the word consuming understates what is actually happening. As gas, dust, torn apart stars, and other material fall toward a supermassive black hole, they do not fall in cleanly and quietly the way water spirals down a drain. Instead, they form a structure called an accretion disk, a vast, flattened swirl of superheated material orbiting the black hole at tremendous speeds, compressed and heated by friction and gravitational forces to temperatures of millions of degrees Celsius. The disk glows with an intensity that can dwarf entire galaxies containing hundreds of billions of stars, and the magnetic fields threading through it launch jets of plasma and radiation outward from the poles at velocities approaching the speed of light. The black hole itself, remember, is not luminous. Nothing escapes from inside the event horizon. Not light, not radiation, not information of any kind. The spectacular energy output of a quasar comes entirely from material that has not yet crossed that threshold from the infalling matter heating itself to incandescence in the region just outside the point of no return. In a sense, a quasar is a black hole announcing its meals to the entire observable universe, and TON 618 was, during the period we can observe it, one of the loudest diners in cosmic history. Its luminosity, the total energy output across all wavelengths, reaches approximately 4 × 10⁻40 watts. To put that number into any kind of human context, though numbers at this scale resist human intuition almost by definition, it is roughly 140 trillion times brighter than our Sunday. Let that sit for a moment. 140 trillion suns, all burning simultaneously, all pouring their energy out into the cosmos, and you still have not matched what TON 618 was doing at its peak. Our entire Milky Way galaxy, with its hundreds of billions of stars, produces a fraction of the energy that TON 618 alone was radiating from a region smaller than our solar system. The accretion disk around that central black hole, this disk of superheated, electromagnetically tortured gas, outshined the combined output of everything in a galaxy by a factor that makes the word outshined feel almost embarrassingly inadequate. But the luminosity, as staggering as it is not what makes TON 618 the object that keeps astrophysicists quietly disturbed when they run the numbers at night. What is genuinely unnerving about TON 618 is the thing at its center. To understand why TON 618's central black hole is so alarming, you need a sense of scale. And black hole scales are notoriously resistant to any analogy that doesn't eventually collapse under its own absurdity. But let's try. Our Sun, the star at the center of our solar system, the thing that makes photosynthesis happen and keeps us from drifting frozen through interstellar space, has a mass of roughly 2 × 10⁻30 kilograms. That number is itself incomprehensible, but astronomers use it as a unit, the solar mass, as a convenient way to compare stellar objects to one another. A star with a mass of 5 solar masses is 5 times heavier than our Sunday, straightforward enough. The black hole at the center of our own Milky Way galaxy is called Sagittarius A star. It sits about 26,000 light-years from Earth, tucked into the dense heart of our galaxy, and it has a mass of approximately 4 million solar masses, 4 million times heavier than the Sunday. It is, by any earthly standard, an object of almost incomprehensible size. Its event horizon, the spherical boundary, beyond which nothing can escape, spans about 24 million kilometers in diameter. The distance from Earth to the Moon is roughly 384,000 kilometers, meaning Sagittarius A star's event horizon spans about 60 times that distance across. It is large enough that if you placed it where our Sun is, the event horizon alone would extend about 1/6 of the way to Mercury. And yet Sagittarius A star, for all its mass and gravitational menace, is a sleeper. It is not currently an active quasar. It sits relatively quiet at the center of our galaxy, occasionally flaring when a gas cloud or a star passes close enough to feed it a small meal, but mostly dormant in the way that a volcano between eruptions is dormant, not gone, not harmless, but not actively consuming and radiating at full power. TON 618 has a mass of approximately 66 billion solar masses, not 66 million, billion, 66,000 million solar masses concentrated into a single object. Sagittarius A star at 4 million solar masses sounds impressive until you remember that TON 618 is roughly 16,500 times more massive. If you wanted to build TON 618 out of Sagittarius A star-sized black holes, you would need more than 16,000 of them. 16,000 copies of the largest, most gravitationally dominant object in our galaxy merged together, and you would be approaching the mass of TON 618's central engine. The event horizon of a black hole, the Schwarzschild radius, the point of no return, scales directly with mass. Double the mass, double the radius. And so, because TON 618's black hole is so enormously more massive than anything we have in our neighborhood of the cosmos, its event horizon is correspondingly enormous. The Schwarzschild radius of TON 618's black hole is approximately 1,300 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, roughly 150 million kilometers. TON 618's event horizon, therefore, has a radius of about 1,300 times the Earth-Sun distance, meaning the diameter of just the event horizon alone, the sphere inside which nothing can escape, is roughly 2,600 times the distance from the Earth to the Sunday. For comparison, Neptune, the outermost major planet in our solar system, orbits at about 30 astronomical units from the Sunday. The event horizon of TON 618 would swallow Neptune's orbit with room to spare on every side. The entire volume of space, enclosed by Neptune's orbit around our Sun, everything from the inner planets, through the asteroid belt, through the gas giants and the ice giants, out to Neptune, would fit inside TON 618's event horizon, roughly 43 times over. Light travels at 299,792 kilometers per second. Nothing moves faster. And yet, light racing at full speed across the diameter of TON 618's event horizon would take approximately 22 days to make that crossing. 22 days of traveling at the ultimate speed limit of the universe, and you still have not crossed the event horizon. You are still inside. You cannot escape. The gravity has you, and it had you the moment you crossed that boundary, and no amount of thrust, no amount of energy, no conceivable technology could claw back what the black hole's gravity has taken. This is not a metaphor or an approximation. This is geometry applied to mass. This is what happens when you pack 66 billion solar masses into a singularity and let general relativity describe the space around it. The math produces numbers that feel like science fiction, but the universe did not ask our permission before building this thing. At this point in the story, a reasonable question is how anyone could possibly know the mass of an object 10.4 billion light-years from Earth. We cannot send a probe. We cannot orbit a satellite around it. We cannot drop anything into it and measure how long it takes to fall. The number 66 billion solar masses does not come from direct observation in any sense that feels intuitive. It comes from physics and from light, which has always been the only messenger that the distant universe can send us. The method used to determine TON 618's mass is called the virial mass method, and it relies on a relationship between the motion of gas in the broad line region surrounding a quasar's central black hole and the gravitational pull of that black hole. Here's the logic. Gas clouds orbiting near the black hole move at speeds determined by how much gravitational force is pulling on them. More mass means stronger gravity, means faster orbital speeds. The faster the gas moves, the more it Doppler shifts the spectral lines in the light it emits, Some gas on the side moving toward us has its lines shifted blue, toward shorter wavelengths, while gas moving away shifts red, toward longer wavelengths. The result is that spectral lines from the broad line region appear broadened, smeared across a range of wavelengths that reflects the range of velocities in the gas. By measuring how broad those spectral lines are, astronomers can infer the velocity dispersion, the range of speeds of the gas in that region. And once you know how fast something is orbiting, and you know from other measurements how far it is from the center, you can calculate the mass of the central object using the same orbital mechanics that Kepler worked out centuries ago for the planets in our solar system. The same physics that governs Earth's orbit around the Sun governs gas clouds orbiting a billion solar mass black hole. Scale changes. Physics does not. The broad line region around TON 618, the zone of fast-moving gas, whose spectral signatures betray the black hole's mass, spans roughly 1 light-year across. 1 light-year, remember, is roughly 9.46 trillion kilometers. The gas moving within that light-year-wide zone is traveling fast enough, under the gravitational influence of that central mass, to produce spectral line widths that, when plugged into the virial mass calculation, spit out 66 billion solar masses. This is not a wild guess. It is an application of well-understood, thoroughly tested physics to light that has been traveling for 10.4 billion years. The uncertainty in the measurement matters. Mass measurements of distant quasars carry uncertainty factors that can be significant. But even accounting for those uncertainties, TON 618's central black hole is, without question, one of the most massive objects in the observable universe. And that word observable is doing important work in that sentence. The observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, contains something on the order of 2 trillion galaxies. 2 trillion. Of those, we have measured the black hole masses in a relatively tiny fraction. The odds that TON 618 is the single most massive black hole that exists anywhere in the universe are not great. The odds that there are objects we simply cannot yet see or cannot yet measure that dwarf even TON 618 inches mass are not small. What we can say with confidence is that within the observable universe, in the catalogue of objects whose masses we have actually been able to estimate, TON 618 sits at or very near the top of the list. Astronomers have a naming problem when it comes to black holes, because the category supermassive has effectively been stretched beyond usefulness. Technically, any black hole with a mass greater than 1 million solar masses qualifies as supermassive. Sagittarius A* at 4 million solar masses is supermassive. The black hole at the center of the Andromeda galaxy, at about 140 million solar masses, is supermassive. The black hole in the giant elliptical galaxy, M87, the one that produced the first ever directly imaged black hole shadow in 2019, has a mass of about 6.5 billion solar masses and is also technically supermassive. TON 618 at 66 billion solar masses is supermassive in the same sense that the Pacific Ocean is wet. The category label is technically correct and practically useless as a descriptor. For this reason, some astrophysicists have begun using the term ultramassive for black holes with masses above approximately 10 billion solar masses, though the boundary is not formally defined and the term is not universally adopted. TON 618 falls comfortably within whatever definition of ultramassive you care to use. It is, in a meaningful sense, in a category of its own not just because it is the heaviest known, but because its mass sits at or near the theoretical limits that physicists have worked out for how massive a black hole can realistically become. There is an upper limit, at least in theory. As a black hole grows more massive, the accretion disk surrounding it becomes increasingly unstable. Very massive black holes eat less efficiently, the accretion rate drops, the luminosity relative to mass decreases, and the process of growth slows. There is a theoretical maximum luminosity for a given black hole mass, called the Eddington luminosity, beyond which radiation pressure from the disk would blow away the infalling gas before it could be consumed, effectively putting a speed limit on how fast a black hole can eat. The Eddington luminosity scales with mass, and for a black hole the size of Ton 618s, it still implies an absolutely staggering rate of energy output, but it also implies that there is a ceiling, somewhere up there, that black holes cannot exceed. Ton 618's mass sits near what some models suggest is the practical upper limit achievable through the standard processes of quasar feeding over cosmic time. Growing a 6 billion solar mass black hole is not a quick process, even by astronomical standards. It requires billions of years of active feeding, or a series of mergers with other massive black holes, or both. And it has to happen efficiently enough, early enough in the universe's history, that by the time we see Ton 618 as it appeared 10.4 billion years ago, the growth has already happened. All that eating, all that growth, all that mass accumulation, it predates the light we are seeing now. Other objects in the ultramassive neighborhood deserve mention because they round out the picture. The galaxy cluster Home 15A contains a black hole with an estimated mass of around 40 billion solar masses, comparable to Ton 618 inches mass. Though different in character, sitting much closer to us at roughly 700 million light-years rather than 10.4 billion. The galaxy, NGC 1600, an isolated elliptical galaxy in a relatively quiet cosmic environment, hosts a black hole of about 17 billion solar masses, surprising astronomers when measured because large black holes were not expected to be found in isolated, low-density galactic environments. And there are objects designated as OJ 287, actually a binary quasar system, where two supermassive black holes orbit each other, the larger of which carries a mass of roughly 18 billion solar masses that produces periodic flares as the smaller black hole plunges through the accretion disk of the larger one. Ton 618 outruns all of them, and yet all of them together suggest that the extreme upper end of the black hole mass scale is, if not crowded, at least not entirely empty. A dormant black hole, as terrifying as its gravitational reality is, has a characteristic that makes it navigable in theory, if not in practice. It does not radiate. It does not actively reach out into the surrounding universe and vaporize things. It pulls things toward it, yes, and that pull becomes catastrophic at close range. But at a sufficient distance, and sufficient here means billions of times the event horizon radius, you can orbit a black hole safely, just as Earth orbits the Sun without being consumed by it. A dormant black hole is a gravitational fact, an extreme one, but a passive one. A quasar is a different animal entirely. When a black hole is actively feeding when an accretion disk has formed and material is falling inward, heating to millions of degrees, and being converted into raw electromagnetic energy with an efficiency that nuclear fusion in stars cannot match the surrounding space, is not safe at any distance that would feel comfortable. The radiation output of an active quasar like Ton 618, operating at its observed luminosity, would sterilize space across vast distances. The intense ultraviolet radiation, X-rays, and gamma rays pouring out of the accretion disk and from the relativistic jets launched from the poles would strip electrons from atoms, disrupt molecular chemistry, destroy the organic compounds that form the building blocks of life, and heat gas to temperatures where planetary atmospheres would be blasted away. At the distance of 1 light-year from Ton 618, still enormously far from the event horizon itself, the intensity of radiation would be devastating by any biological standard. Planets orbiting stars that had the misfortune of existing within a certain radius of a quasar as active as Ton 618 would be subject to a continuous bombardment of high-energy radiation, far exceeding anything that life as we understand it could survive. The concept of a habitable zone around a star becomes meaningless when the local quasar is washing everything with the electromagnetic equivalent of a permanent impossible to block, X-ray source many orders of magnitude more intense than the star itself. The jets compound this picture. Quasar jets, the relativistic streams of plasma launched perpendicular to the accretion disk, can extend for millions of light-years from the central source, traveling at velocities that can exceed 99% of the speed of light. Anything in the path of such a jet is subjected to particle bombardment and radiation exposure that would be lethal at ranges that dwarf the size of entire galaxy clusters. The jets of some quasars have been observed to reach lengths of millions of light-years. While TON 618's jet geometry is not as precisely mapped as some nearby quasars, the physics that drives jet formation is universal, and at TON 618's luminosity and mass, the jets would be among the most energetic structures in the observable universe. A dormant black hole, then, is a gravitational hazard, dangerous if you approach it, but spatially limited in its direct effects. A quasar is an environmental hazard, a radiative hazard, a thing that does not need to touch you to affect you, because it has turned the space around it into an inhospitable radiation environment, spanning distances that would take generations traveling at the speed of light to cross. A quasar at TON 618 scale is not merely worse than a dormant black hole in some abstract academic sense. It is worse in the sense that it actively transforms the nature of the space it occupies, poisoning the cosmic environment across volumes that no black hole in quiet mode could ever threaten. Let's spend some time at the edge of TON 618, at least conceptually, because the physics of what happens near an ultramassive black hole of this scale produces some genuinely strange results that push against our intuitions in interesting ways. The common picture most people carry of a black hole is the terrifying singularity of dense, compressed matter, with gravity so strong that approaching it means being stretched vertically while compressed horizontally, a process physicists call spaghettification, which is both the most accurate and most whimsically named technical term in astrophysics. The tidal force responsible for spaghettification comes from the difference in gravitational pull between the near side and the far side of an object as it falls toward the black hole. The near side is pulled more strongly than the far side, and that differential pull stretches the object along the radial direction while squeezing it perpendicular to it. Here is what surprises most people about TON 618's black hole specifically. At the event horizon itself, the tidal forces are not especially powerful, not by the standards of smaller black holes. This seems counterintuitive. The event horizon of a 6 billion solar mass black hole should be more extreme than the event horizon of a smaller one, right? But the tidal force at the event horizon depends on the black hole's mass in a non-obvious way. For smaller black holes, the event horizon is relatively close to the singularity, and the gradient of gravity across that region is steep. You experience enormous tidal forces. For very massive black holes, the event horizon is so far from the singularity that the curvature of spacetime at the horizon itself is relatively gentle. The gradient is shallower because you are calculating tidal forces over the same human body length, but at a radius that is vastly larger. At TON 618's event horizon, a person-sized object falling inward would not immediately feel the tidal spaghettification that smaller black holes would impose near their horizons. The tidal forces there are, by black hole standards, relatively mild. You might cross the event horizon without immediately realizing you had done so. There would be no physical marker, no visible boundary, no sensation of crossing a threshold. The light from outside would still reach you. It would be increasingly blue-shifted as it fell inward toward you, concentrated and energized by the black hole's gravity, but you would still receive it. The universe outside would still be visible, but you could not go back. That is the defining fact of the event horizon, not what it feels like to cross it, but what crossing it means. From the moment you pass that boundary, every possible path through spacetime that your future could take curves inevitably inward toward the singularity. The structure of space-time inside the event horizon is such that moving toward the singularity is as unavoidable as moving forward in time. Time itself, in a sense, flows toward the center. No future you can navigate leads back out. The radiation and pressure of the infalling material and the extreme environment surrounding Ton 618's actively feeding black hole would certainly kill you long before you reach the event horizon in any realistic scenario. But the point is that the geometry of the crossing, for a black hole this size, is counterintuitively quiet. The universe outside, viewed from inside the event horizon, would appear distorted in extraordinary ways. Light from the entire outside universe would be gathered and focused into a shrinking disk above you as you fell inward, an effect called the photon sphere, the region where light travels in circular orbits. You would see the entire observable universe compressed into a shrinking circle above your head, its colors increasingly blue-shifted, its photons increasingly energetic, as you fell toward a fate that physics made certain at the moment you crossed that line. The time dilation at that boundary is equally remarkable. To an outside observer, if any outside observer could see you, which they cannot, because light cannot escape back out your passage through the event horizon, would appear to slow to a stop. You would appear to freeze at the boundary, gradually redshifting into invisibility as the last photons you emitted before crossing took longer and longer to climb out of the gravitational well. You would effectively disappear from the observable universe without ever appearing to cross the threshold. Your clock, from your perspective, continues normally. From the universe's perspective, you simply vanished. Ton 618 exists, or rather existed, because what we see is its past during a period of cosmic history that astronomers call the epoch of peak quasar activity. The universe has a history of quasar abundance, and that history shows a very clear pattern. Quasars were far more common in the early universe than they are today. When the universe was between about 1 and 3 billion years old, a period that corresponds to redshifts roughly between 2 and 6 on the cosmological scale, the density of quasars was orders of magnitude higher than it is. In the universe we inhabit now, galaxies were younger. Their central black holes were still actively feeding on the abundant gas that had not yet been converted into stars, and the conditions for sustaining massive accretion disks were present across a much larger fraction of the galaxy population. Ton 618 lies at a redshift of 2.219, placing it squarely in this peak epoch. The universe it exists in is one where quasars are a common sight in any deep-field astronomical image, where the dense, gas-rich conditions of early galaxy formation provide the raw material that black holes need to grow rapidly. That same universe, remember, is not the universe we live in today. The universe of 3.3 billion years after the Big Bang Ton 618's era was fundamentally different from the universe of 13.8 billion years after the Big Bang, which is when you are reading or hearing these words. In the modern universe, active quasars are rare. The closest quasar to Earth is 3C273, lying at a distance of about 2.4 billion light-years, still cosmologically close relative to Ton 618, and it is considered reasonably bright for what it is. But even 3C273 operates at a luminosity far below Ton 618's peak output. The modern universe's quasars are, in general, quieter, less common, and found at much lower accretion rates than their early universe counterparts. The abundant gas that fueled the great feeding frenzy of early cosmic history has mostly been converted into stars, swept up into galaxies, or otherwise consumed. The supply lines have thinned. What replaced the quasar era in the modern universe? Dormant supermassive black holes, sitting quietly at the centers of galaxies, their accretion disks starved of new material, waiting. Every large galaxy we have examined appears to contain a supermassive black hole at its core, and in most of those galaxies, the black hole is dormant or only mildly active. The correlation between galaxy size and central black hole mass is one of the most remarkable relationships in observational astronomy. Larger galaxies tend to have more massive central black holes, in a ratio that holds across many orders of magnitude and many different galaxy types, suggesting that the growth of galaxies and the growth of their central black holes are tightly coupled processes that co-evolved through the history of the universe. What this means, in an almost poetic sense, is that every galaxy you see in the night sky likely once hosted a quasar. Our Milky Way almost certainly went through an active quasar phase in its youth, when Sagittarius A star was feeding rapidly on the dense gas of the early galaxy. That phase ended billions of years ago. What remains is the evidence of 4 million solar mass black hole sitting quietly in the galactic center, the spent engine of a cosmic fire that burned bright and then went dark. Somewhere, 10.5 billion light-years away, what became of TON 618 after the snapshot we see? Almost certainly, the quasar phase ended. The gas supply thinned. The accretion disk faded. The blinding luminosity dimmed over millions or billions of years. What remained was the black hole 66 billion solar masses of gravitational reality sitting at the center of whatever galaxy TON 618 occupied, in a universe that had grown calmer and quieter around it. Whether that galaxy still exists, whether it merged with others, whether TON 618's descendant black hole is even larger now, these are things we cannot observe, because the light that would tell us that story has not yet had time to reach us. We can only see what it was, not what it became. One of the genuinely fascinating aspects of TON 618's scale is that it brushes against theoretical limits, the edges of what physics says is possible, at least through the standard mechanisms we understand. The Eddington limit, mentioned earlier in connection with how fast a black hole can feed, is one such constraint. Named after the British astrophysicist Arthur Eddington, it represents the balance point between gravity pulling material inward and radiation pressure pushing it outward. When a black hole feeds, the accretion disk radiates enormously, and that radiation pushes on the infalling gas. At the Eddington luminosity, which scales with the black hole's mass, the outward radiation pressure exactly balances the inward gravitational pull. Exceed this luminosity and the radiation blows away the incoming gas, shutting down the accretion process. Operate below it and accretion can proceed. In practice, black holes can temporarily exceed the Eddington limit, the super-Eddington accretion regime, though this typically leads to more complex behavior in the disk and is not easily sustained over long periods. And the Eddington limit is not a hard wall that nothing in nature ever crosses, it is more of a soft ceiling with some wiggle room in the right conditions. But the Eddington limit does constrain how fast a black hole can grow. A black hole feeding at exactly the Eddington rate, the maximum sustained rate, has an E-folding time of about 450 million years. An E-folding time is the time it takes to increase in mass by a factor of about 2.718, the mathematical constant E. Doubling in mass takes slightly longer, about 300 million years. Starting from a seed black hole of 100 solar masses, the kind left behind by the collapse of very massive early stars, and growing at the maximum sustained Eddington rate, you can calculate how long it takes to reach 66 billion solar masses. The answer comes out to roughly 50 E-folding times, or somewhere around 20 to 25 billion years of continuous Eddington rate feeding. But the universe is only 13.8 billion years old. And TON 618 was already at 66 billion solar masses when the universe was only 3.3 billion years old. That is the problem that TON 618 and other massive early quasars pose for our models of black hole growth. There does not seem to be enough time, under standard growth mechanisms, to build a black hole this massive this early. Theoretical solutions exist, and physicists have proposed a range of them with varying degrees of observational support, but none of them is fully satisfying. One possibility is that the seed black holes from which these monsters grew were themselves very massive, not the 100 solar mass stellar remnants that serve as the starting point in the simplest models, but objects of perhaps 1 million solar masses formed directly from the collapse of enormous gas clouds in the early universe without going through normal stellar evolution at all. These hypothetical, direct collapse black holes would shorten the growth timeline considerably. Another possibility is that early black holes went through periods of super-Eddington accretion, growing faster than the standard limit would suggest in episodes fed by the rich gas environments of the young universe. A third possibility is that galaxy and black hole mergers played a more significant role than models have assumed, with multiple massive black holes combining to produce the ultramassive objects we observe. The honest answer is that we do not fully know. TON 618's existence is, in part, an unresolved puzzle, a data point that does not fit cleanly into our existing framework for how black holes grow, and that tells us something important is missing or underestimated in our theoretical models. This is one of the reasons astronomers find objects like TON 618 so compelling. They are not just astonishing for their size. They are challenging for what their size implies that the universe figured out how to build something this large in a time frame that our physics struggles to accommodate. The broad line region, the zone of rapidly orbiting gas whose spectral signatures allow us to measure TON 618's black hole mass, is itself a remarkable structure worth dwelling on for a moment. Surrounding the accretion disk of a quasar, at distances ranging from light days to light years from the central black hole, is a population of gas clouds moving at velocities of thousands to tens of thousands of kilometers per second. These clouds are photoionized, energized by the intense radiation from the accretion disk, causing their atoms to lose electrons and emit light at specific wavelengths when those electrons recapture. The spectral lines they produce hydrogen's Balmer series, carbon, magnesium, oxygen, and other elements appear broad in the quasar's spectrum because the clouds are moving at such different velocities relative to us, some rushing toward us at enormous speeds and some rushing away. In TON 618's case, the broad line region spans approximately 1 light-year in radius. 1 light-year, the zone of gas whose motions encode the gravitational signature of the central black hole, is an entire light-year across a volume of space that contains approximately 63,000 astronomical units. If you placed our entire solar system at the center of TON 618's broad line region, Proxima Centauri, the nearest star to our Sun, would sit roughly at the edge of it. The gravitational influence of 66 billion solar masses extends meaningfully across a distance that encompasses the nearest stellar neighborhood. The velocity of the gas in this region, the numbers that translate, through the virial mass equation, into the 66 billion solar mass figure, is in the range of several thousand kilometers per second. For context, Earth orbits the Sun at about 30 kilometers per second. Spacecraft launched at escape velocity from Earth leave at a bit over 11 kilometers per second. Voyager 1, humanity's fastest object, travels at about 17 kilometers per second relative to the Sunday. Gas in TON 618's broad line region moves at roughly 100 to 500 times that speed, all of it governed by the gravitational grip of the black hole at the center. The measurement chain that connects this observation to a mass from spectral line width to velocity dispersion to orbital velocity to central mass has been validated extensively in cases where we have alternative ways to check the result. It is not an ad hoc method invented specifically for distant quasars. It is an application of tested orbital dynamics to a new and extreme regime. The result, 66 billion solar masses, carries uncertainty, but the uncertainty does not change the fundamental conclusion. This is a black hole, unlike anything in our cosmic neighborhood, and it is among the most massive objects the observable universe contains. There is a fundamental challenge in communicating anything about objects at TON 618's scale, and it deserves direct acknowledgement rather than the usual strategy of stacking astronomical fact upon astronomical fact without pause. Human intuition evolved to handle distances measured in meters and kilometers, masses measured in kilograms, and timescales measured in days and years. The numbers that describe TON 618 are not merely large in the way that the national debt is large, or the number of grains of sand on all of Earth's beaches is large. They are large in a way that genuinely breaks the analogy-making machinery of the human mind. You can say that 140 trillion suns worth of energy pours out of Ton 618 every second, and the sentence is technically accurate, but it does not land with the same weight as saying that a particular mountain is taller than you expected. Your nervous system has calibrated emotional responses to earthly scales. There is no evolved response to 140 trillion suns. What works better, psychologically, is not trying to make the numbers feel comfortable, but instead letting the discomfort itself be the message. The reason TON 618 is genuinely fascinating, the reason astronomers who work on quasar physics sometimes describe a kind of intellectual vertigo when they spend too long with the numbers, is precisely that it resists comprehension. The universe built something that exceeds the categories our brains developed to handle. That is not a limitation of the universe. It is a limitation of primates who spent most of their evolutionary history worrying about predators and food supplies at scales well below the astronomical. The Milky Way galaxy, our entire home, 100,000 light-years across, containing between 100 and 400 billion stars, would look, from the distance of Ton 618, like a point of light that requires a large telescope to even separate from the background noise. The entire galaxy, with its spiral arms and its stellar nurseries and its 100 billion worlds, would be a single, unresolved smear in a distant image. Ton 618's accretion disk, in the same image, would outshine it. The entire Milky Way, outshined by a disk of hot gas around a single object. That is not metaphor, that is the physics. 10.4 billion light-years. The distance to Ton 618 is worth sitting with separately from all the other numbers, because it introduces a temporal dimension that the purely spatial description misses. A light-year is not just a unit of distance, it is a unit of time encoded in space. When you observe something 1 light-year away, you see it as it was 1 year ago. When you observe something 10 light-years away, you see it as it was 10 years ago. At 4 light-years, roughly the distance to Proxima Centauri, you see the nearest star as it appeared 4 years in the past. At 26,000 light-years, the distance to Sagittarius A star, you see the galactic center as it was 26,000 years ago, when modern humans were navigating the tail end of the last ice age. At 10.4 billion light-years, the distance to TON 618, you are looking at a snapshot of the universe from 10.4 billion years ago, when the cosmos was roughly a quarter of its current age. The light that enters your telescope today, or your eyes if you could see it without instruments, departed from the vicinity of Ton 618 before the Earth existed, before the Sun existed, before most of the stars in our part of the galaxy had even formed. It traveled through a universe that was continuously expanding around it, stretching the very fabric of space through which it moved, carrying that stretching as the cosmological redshift that Burbage and her colleagues measured when they took Ton 618's spectrum in 1970. This means something important about the nature of what we know. We are not observing Ton 618 as it is now. We have no idea what Ton 618 is now. The quasar may have shut down billions of years ago. The black hole at its center may have merged with other black holes, growing still larger. The host galaxy may have collided with other galaxies, triggering new star formation or stripping away gas. Ton 618 as it currently exists is, in a cosmic sense, completely unknown to us. The universe has continued its business for 10.4 billion years since that light departed, and none of that subsequent history has had time to reach us. The only thing we have is the snapshot, the frozen moment of 10.4 billion years ago, preserved in the electromagnetic radiation that has been traveling toward us ever since. It is the most ancient document in human science, older than the Sun, older than the Earth, older than anything biological that has ever existed. And what it shows us is a burning, ultramassive feeding machine operating at luminosities that no other object in the observable universe surpasses. There is a human dimension to the Ton 618 story that tends to get lost in the spectacle of the numbers, and it is worth recovering. The Tonantzintla Observatory was established in the 1940s as part of a collaboration between Mexican astronomers and their international colleagues, driven in large part by the efforts of Luis Enrique Erro, a Mexican diplomat and astronomer who campaigned tirelessly to give Mexico a world-class astronomical facility. Erro recognized that the Mexican highlands offered exceptional observing conditions, clear skies, low humidity, high elevation that would make the site competitive with the great observatories of the Northern Hemisphere. The catalogue that bears the observatory's name, the Tonantzintla catalogue, producing the Ton prefix in Ton 618, was built over years of painstaking photographic work, with astronomers and their assistants reviewing thousands of glass photographic plates by eye, looking for objects that differed in color or appearance from ordinary stars. Entry 618 was one of tens of thousands of objects catalogued in this way, a single entry in a list, notable only for the fact that it appeared slightly bluer than average, a characteristic that, decades later, would reveal it as one of the most extraordinary objects ever identified. The Tonantzintla plates were not high resolution by modern standards. The photographic emulsions of the 1950s captured the sky with a sensitivity and precision that modern digital detectors make look quaint. The blue appearance of what would become Ton 618 was not a dramatic signal, it was a subtle statistical deviation from the expected color of a star, the kind of thing that required trained eyes and careful attention to notice at all. And yet someone noticed. The catalogue was built. The number 618 was assigned to that patch of blue in the sky, and it sat there, waiting, until better instruments and better physics could reveal what it actually was. There is something worth honoring in that, in the unglamorous, essential labor of catalogue making that underpins essentially all of observational astronomy. The discoveries that make headlines, the measurements that reshape our understanding of the universe, almost always rest on earlier, less celebrated work by people who gathered data without knowing exactly what they were gathering. Ton 618's fame rests, in part, on the shoulders of the people in Tonantzintla who photographed that corner of the sky and wrote down a number without knowing that they were, in some small sense, leaving a marker on the most massive black hole that anyone would ever find. Ton 618 is not just an isolated record holder. It sits at the intersection of several of the most active and contested areas of modern astrophysics, each of which bears on the question of what the universe is and how it got to be the way it is. The relationship between supermassive black holes and the galaxies they inhabit is one of the great mysteries of modern cosmology. Galaxies and their central black holes appear to grow together, in a relationship that the data makes clear, but the mechanisms behind which remain subjects of active research. The mass of a central black hole correlates with the properties of the galaxy surrounding it, particularly the mass and velocity dispersion of the galaxy's central bulge in ways that are too tight to be coincidental. Whatever process drives galaxy formation also drives black hole growth, and they seem to regulate each other in a feedback loop that astronomers call AGN feedback, where AGN stands for active galactic nucleus. The basic idea of AGN feedback is that when a central black hole is actively feeding, when it is a quasar, the energy it dumps into the surrounding galaxy through radiation, winds, and jets can heat and expel the gas that would otherwise form new stars. This heating can effectively quench star formation across the entire galaxy, shutting down the galaxy's growth. And as the star formation shuts down, the gas supply to the black hole eventually thins, dimming the quasar and allowing the galaxy to evolve more quietly. In this view, quasars are not just spectacular phenomena, they are regulatory mechanisms, the universe's way of controlling how fast galaxies grow and how efficiently they convert gas into stars. Ton 618, at its observed luminosity, was almost certainly doing exactly this, pumping so much energy into its surrounding galaxy that star formation would have been heavily suppressed or quenched across much of the host galaxy. The galaxy around an object as luminous as Ton 618 would have been bathed in radiation and swept by energetic winds and jets that heated the interstellar medium, made it less susceptible to gravitational collapse into new stars, and potentially expelled significant quantities of gas from the galaxy's disk altogether. This is not academic. It is the reason galaxies like ours look the way they do today. The Milky Way's current rate of star formation, a few solar masses per year, is relatively modest compared to what it was in the early universe. The quasar phase that Sagittarius A star went through billions of years ago almost certainly played a role in transitioning our galaxy from its vigorous early star-forming state to the more sedate system it has become. TON 618, observed at a moment of extraordinary activity in the early universe, is a glimpse into a process that shaped essentially every large galaxy we can see today. At the center of every black hole, according to general relativity, lies a singularity, a point, or, in the case of rotating black holes, a ring, where density becomes mathematically infinite and the curvature of space-time diverges without bound. General relativity, Einstein's theory of gravity, which has passed every observational test thrown at it with extraordinary precision, predicts this singularity and then, in a sense, stops. The equations break down at the singularity. The output is infinity, which in physics generally means we have run out of theory, rather than this is what actually happens. What actually happens at the singularity of a real black hole is not known. The consensus view among physicists is that a quantum theory of gravity, a framework that extends and supersedes general relativity at extreme scales, the way quantum mechanics extended and superseded classical mechanics would, resolve the singularity into something finite and physically meaningful. The singularity, in this view, is not a feature of reality, but a limitation of our current theoretical framework. But no complete, experimentally verified quantum theory of gravity exists. String theory and loop quantum gravity are the leading contenders, both mathematical frameworks of extraordinary sophistication that make progress on the problem but have not yet yielded predictions that experiments can definitively test. The singularity at the center of TON 618's black hole, or at the center of any black hole, remains one of the deepest unsolved problems in physics. This is worth dwelling on because it is easy to miss amid all the impressive numbers. TON 618 is not just a spectacular object. It is a place where our best understanding of physics, the theoretical framework that built the modern technological world, reaches its limits and admits ignorance. Inside that event horizon, at the singularity, something happens that no living physicist fully understands. The universe contains a region where matter goes in and does not come out, and what becomes of it once it crosses that threshold is genuinely unknown. Some theoretical proposals have suggested that information swallowed by a black hole is not truly lost, that quantum mechanics, properly applied to black holes, would require that the information encoded in whatever falls in must, in some scrambled and highly non-obvious form, eventually leak back out through a process called Hawking radiation. Stephen Hawking proposed in 1974 that quantum effects near the event horizon would cause black holes to slowly radiate energy, a thermal radiation generated by quantum vacuum fluctuations at the horizon, and that over vastly long timescales, a black hole would slowly evaporate through this process. For a black hole the mass of TON 618's 66 billion solar masses, the Hawking temperature is so incredibly low and the timescale for evaporation so astronomically long that the effect is utterly negligible on any timescale remotely connected to the current age of the universe. The Hawking evaporation time for a black hole of this mass is many orders of magnitude longer than the current age of the universe. TON 618's black hole, assuming it stopped accreting mass entirely, would take an incomprehensibly long time to evaporate through Hawking radiation, far longer than the universe has existed, longer than any conventional measure of time feels meaningful to invoke. But the principle is what matters. Hawking radiation, if it is real, and most physicists believe it is, though it has never been directly detected because it is so faint, would mean that black holes are not eternal. They are long-lived but not immortal. Even TON 618's ultramassive heart, in the fullness of cosmic time, is not permanent. It is, by the standards of the universe's lifespan when properly measured in the trillions and quadrillions of years that stellar physics and thermodynamics project, a temporary structure. The universe plays long games. The information paradox that Hawking radiation introduced is worth exploring further, because it sits at the junction of the two greatest theories in physics and remains genuinely unresolved in ways that matter for understanding what black holes are at a fundamental level. Quantum mechanics holds, as one of its foundational principles, that information is conserved. If you know the complete quantum state of a physical system at one moment, you can, in principle, calculate the complete quantum state at any earlier or later moment. Information can be scrambled and transformed, but it cannot be destroyed. This is called unitarity, and it is not a minor technical point. It is one of the deepest structural features of quantum mechanics, built into the mathematical framework in a way that cannot be cleanly removed without unraveling the whole theory. General relativity, on the other hand, produces black holes with event horizons that appear to destroy information irreversibly. Whatever falls in permanently. The information about the initial state of the infalling material seems to be lost, crushed to the singularity, hidden behind a horizon that nothing can cross outward, effectively erased from the universe's ledger. When Hawking proposed that black holes radiate thermally, the radiation he described was precisely thermal random, carrying no information about what fell in beyond the black hole's overall mass, charge, and rotation. A black hole formed from collapsed hydrogen gas and a black hole formed from the same mass of old stars and dust and radiation would, if Hawking's original formulation was correct, produce identical Hawking radiation as they evaporated. The information about how they were formed would be gone. This is the information paradox. Quantum mechanics says information must be preserved. General relativity, combined with quantum field theory, in Hawking's original calculation, says it is destroyed. Both theories cannot be right, and both theories have experimental support that makes dismissing either one completely impossible. The resolution, whatever it turns out to be, will almost certainly require quantum gravity, the unfinished theory that physicists have been working toward for decades. Some proposals, like the fuzzball descriptions from string theory, suggest that the event horizon is not the clean geometric boundary it appears to be in general relativity, but rather a fuzzy quantum structure that gradually encodes and releases information. Others, like the firewall proposal introduced in 2012, suggest that the event horizon must be a region of extremely high energy, where infalling matter is instantly vaporized, which conflicts with the expectation from general relativity that crossing the horizon of a large black hole should be unremarkable from the infaller's perspective. TON 618's black hole, as an extreme example of the class, makes these questions more acute. If the event horizon of a 6.6 billion solar mass black hole is genuinely a gentle, unmarked boundary that infalling matter crosses smoothly, then the firewall proposal has a hard time applying to it. If the event horizon is, at the quantum level, a high-energy barrier, then that must apply to TON 618's horizon as much as to any other. The physics does not negotiate based on the size of the black hole. These are not questions with currently accepted answers. They are the frontier of physics, where the best mathematical minds on Earth have been working for decades and producing proposals of extraordinary ingenuity and sophistication, none of which has yet achieved the status of consensus. The black hole at the center of TON 618 contains, somewhere in its unobservable interior, the answer to some of these questions. The universe knows the answer. We are still working on the problem. Given that TON 618 sits at or near the top of the known black hole mass scale, a natural question is whether anything larger exists or could exist somewhere in the observable universe. The theoretical upper limits for black hole mass are not firmly established. Astrophysicists have proposed various arguments suggesting that black holes above certain masses should be very rare or essentially non-existent through standard formation processes but standard formation processes is doing a lot of work in that sentence. The early universe was a more chaotic, more gas-rich, more densely structured environment than the universe we inhabit today, and formation pathways that might be suppressed in the modern universe could have been viable in the extreme conditions of cosmic youth. The observational challenge is equally significant. The most massive black holes, like TON 618, tend to be the most distant because they were most common during the era of peak quasar activity, which corresponds to high redshifts and large cosmological distances. At those distances, measuring black hole masses requires the spectroscopic techniques described earlier, which have irreducible uncertainties. There could be objects with masses greater than TON 618 that we have observed but misclassified, or measured imprecisely, or simply have not yet turned our instruments toward. The next generation of astronomical observatories, including extremely large ground-based telescopes with primary mirrors spanning 30 meters and above, and space telescopes designed to observe at wavelengths that atmospheric absorption currently blocks, will be able to study quasars at greater distances and with greater spectral precision than is currently possible. The James Webb Space Telescope, operational as of 2022, was designed in part to observe the most distant and earliest galaxies and their active nuclei, probing redshifts that push closer to the cosmic dawn. What Webb and its successors find in the early universe may revise the record books, or it may confirm that TON 618 sits in a class by itself, one of the largest things that the universe, in its particular history, happened to build. There is also the question of intermediate mass black holes, objects in the mass range between stellar black holes of tens of solar masses and supermassive black holes of millions of solar masses, whose existence has been suspected for decades but proven observationally for only a handful of cases. How those intermediate objects factor into the growth histories of the supermassive and ultramassive giants is an active research question with direct implications for understanding how something like TON 618 assembled itself over cosmic time. None of these questions have complete answers today. The pursuit of them drives a significant fraction of modern observational and theoretical astrophysics research. TON 618 is not just a record to be noted and moved past, it is a constraint on models, a testbed for theories, and an object whose existence demands explanation in a way that simpler and less extreme objects do not. There is another way we might eventually learn about the most massive black holes in the universe, and it does not involve light at all. When two massive black holes merge, when two of these ultramassive objects fall toward each other, spiral together, and finally coalesce, they produce ripples in the fabric of spacetime called gravitational waves. Gravitational waves are stretches and squeezes of spacetime geometry itself, propagating outward at the speed of light from the merger event, passing through everything they encounter without being absorbed or scattered by ordinary matter. Unlike electromagnetic radiation, which can be blocked by gas clouds, dust, and the expanding fog of the early universe, gravitational waves carry their information to us essentially unimpeded. The LIGO and Virgo detectors have, since their first detection in 2015, measured gravitational waves from the mergers of stellar mass black holes and neutron stars, objects with masses ranging from a few to a few tens of solar masses. These detections require extraordinary sensitivity. LIGO's mirrors are displaced by less than 1/1000th the diameter of a proton by the waves it detects. But stellar mass mergers produce gravitational waves at frequencies in the range of tens to hundreds of hertz, the audio frequency range, which is what the kilometer-scale arms of LIGO and Virgo are designed to detect. Supermassive and ultramassive black hole mergers, involving objects of millions to billions of solar masses, produce gravitational waves at much lower frequencies, nanohertz frequencies, with wavelengths spanning light years. Detecting those waves requires detectors that span light years, and that is, in a sense, exactly what pulsar timing arrays do. Pulsars, rapidly rotating neutron stars that emit radio beams swept across our line of sight with extraordinary clock-like regularity, can be used as arms of a gravitational wave detector across the galaxy. If a gravitational wave passes through our galaxy, it very slightly stretches and squeezes the distances between us and the pulsars we monitor, introducing tiny timing variations in the pulsar signals. By monitoring dozens of pulsars with radio telescopes over years and decades, correlating the timing variations across the array, astronomers can, in principle, detect the low-frequency gravitational waves produced by supermassive black hole mergers anywhere in the universe. In 2023, multiple pulsar timing array collaborations, including Nanograv in North America and the European Pulsar Timing Array, reported evidence for a gravitational wave background, a kind of cosmic hum of gravitational waves from the accumulation of all the supermassive black hole mergers that have occurred throughout the observable universe. The signal is consistent with what theoretical models predict from the population of merging supermassive black holes across cosmic history. It is, if the interpretation holds up, the first detection of gravitational waves from the ultramassive black hole population, including, perhaps, the echoes of mergers involving objects in TON 618's mass range. Future space-based gravitational wave detectors, particularly the Laser Interferometer Space Antenna LISA, planned for launch in the 2030s, will directly detect gravitational waves from individual supermassive black hole merger events, potentially including mergers involving objects as massive as TON 618. LISA's sensitivity in the millihertz frequency band is designed precisely for this source class. When it operates, we will not just be observing these objects through light, but listening to them through gravitational waves, a second messenger that carries information about their dynamics, their masses, and their spins that electromagnetic observations alone cannot provide. The black holes that built TON 618's universe are, in a sense, still speaking to us. We are only now developing the ears to hear them. There is a perspective on all of this that tends to get overlooked in the technical discussion, and it matters for understanding what observational astronomy actually is. When you look at the night sky with your naked eye, you are looking at the past. The light from the moon left its surface about 1.3 seconds ago. The light from the sun left 8 minutes and 20 seconds ago. The stars, you see those pinpoints of light that seem fixed and eternal, sent their light to you years, decades, or centuries ago. The light from Sirius, the brightest star in the night sky, is about 8.6 years old by the time it reaches your eye. From Betelgeuse, the reddish shoulder of Orion, about 700 years old. The Andromeda galaxy, faintly visible with the naked eye as a smudge in the constellation Andromeda, shows us light that traveled 2.5 million years, light that departed when our ancestors were still evolving, when the species that would become Homo sapiens had not yet emerged. Every telescope, in this sense, is a time machine, not one that allows travel, but one that allows observation of the past, and the further we look, the further back we see. TON 618, at 10.4 billion light-years, takes this principle to an extreme. Looking at TON 618, whether with the instruments that measured its redshift in 1970, or with the modern telescopes that have characterized it more precisely, is looking back 10.4 billion years into a universe that no longer exists as it was then. The universe of TON 618's era had no Sunday, no Earth, no human chemistry, no biology of any kind that we can point to with confidence. It was a universe of gas, dark matter, and rapidly evolving galaxies, denser, hotter, more violently active than anything that exists in our cosmic neighborhood today. The fact that light from that era still reaches us, that photons that departed their source before Earth formed, have been traveling through expanding space for 10.4 billion years and arrived intact at our instruments, is itself worth pausing over. Space expanded around them during that journey, stretching their wavelengths, diluting their energy, but not destroying them. They carried their information through 10.4 billion years of cosmic history and delivered it to a species that had barely existed for 100,000 years and had only developed instruments capable of receiving it in the last few decades. There is something humbling in that exchange. The universe has been conducting this monologue for billions of years, sending out light in all directions, most of which lands nowhere significant and is absorbed or continues traveling indefinitely. A tiny fraction of it, the photons that happened to be aimed at the right coordinates at the right time to intersect with Earth, arrived here, and we noticed. We built machines to capture and analyze those photons. We extracted from them a mass measurement, a luminosity measurement, a redshift, and from those numbers, we reconstructed the story of something 10.4 billion light-years away that burned 66 billion times heavier than our Sunday. The universe did not intend this. The quasar was not performing for us. The light was not sent to us. It was produced in vast, indifferent quantities by a process of matter falling into a gravitational abyss and releasing energy, and some of it ended up pointing in our direction by pure geometry. We are, in that sense, eavesdroppers on a conversation between physics and matter that happened 10 billion years before we existed. Let's slow down for a moment and sit with what Ton 618 is, not in numbers, but in presence. Somewhere in the direction of the constellation Canes Venatici, the hunting dogs, a small and relatively faint constellation between the Big Dipper and the bright star Arcturus, there is a patch of sky that looks, through even a reasonably large amateur telescope, like nothing in particular. The region is not dramatic to the eye. There are no famous nebulae nearby, no bright clusters. It is a quiet corner of sky, unremarkable in appearance, the kind of place an amateur astronomer might skip past in favor of more photogenic targets. Somewhere in that quiet corner, 10.4 billion light-years away, is a black hole that holds 66 billion solar masses and spent billions of years announcing itself to the universe at 140 trillion times the sun's luminosity. Right now, in the present moment, we have no idea what it is. The light carrying information about its current state is still in transit, billions of years away from arrival. By the time it gets here, the sun will be long dead. Earth will be gone, one way or another. Whatever remains of humanity, or of intelligence in general, will be unimaginably different from anything that exists today. In the meantime, the sky in Canes Venatici looks quiet. Just a faint blue point, or rather, the remnant of the light from a faint blue point, catalogued in Mexico in 1957 as entry number 618 by people who did not know what they were looking at. The universe contains these kinds of hidden enormities everywhere we look carefully. The sky that seems empty and quiet at human scales is, at astronomical scales, full of violence and scale and time scales that dwarf everything we have built or experienced or imagined. Ton 618 is the most extreme example we have found so far, but it is an example of a general truth. The universe is far more extreme than its surface appearance suggests, and the more carefully you look, the more extreme it becomes. That is either terrifying or beautiful, depending on your constitution. Most people who spend serious time thinking about it end up deciding it is both. Let's build the scale ladder deliberately, from the familiar to the unimaginable, because the jump from "I understand black holes in general" to "I understand what Ton 618 represents" is not a small one and benefits from being taken in steps. Step 1. A stellar black hole. When a massive star one with roughly 8 or more times the mass of our Sun reaches the end of its nuclear fuel supply, its core collapses under gravity. If the core mass falls in the right range, the collapse produces a neutron star. If the mass exceeds roughly 3 solar masses, the collapse cannot be stopped by any known force, and a black hole forms. These stellar black holes range from about 3 to perhaps 100 solar masses. The black holes first detected by LIGO in 2015, the merger event designated GW150914, involved black holes of approximately 36 and 29 solar masses merging to produce a black hole of about 62. Solar masses. These are stellar-scale objects, dense, gravitationally intense in their immediate vicinity, but small enough that their event horizons span only tens of kilometers. Step 2. Intermediate mass black holes. Between the stellar black holes of tens of solar masses and the supermassive black holes of millions of solar masses, theory predicts intermediate objects, and observations have tentatively identified candidates in the mass range of hundreds to hundreds of thousands of solar masses. The mechanisms by which these form, whether through repeated mergers of stellar black holes in dense clusters, through the collapse of very massive early stars, or through some other process, remain subjects of active debate. Intermediate mass black holes are the missing link in the black hole family tree. Step 3. Supermassive black holes. At galaxy centers, black holes reach masses of millions to billions of solar masses. The black hole in our Milky Way, at 4 million solar masses, is one of the smaller examples. M87's black hole, at 6.5 billion solar masses, is one of the larger ones in our cosmic neighborhood. These objects shaped the evolution of their host galaxies through the AGN feedback process described earlier. Step 4. Ultramassive black holes. At masses above roughly 10 billion solar masses, something changes in character. The dynamics become more extreme. The growth rates become harder to explain. The observational constraints become more difficult to satisfy with standard models. TON 618, at 66 billion solar masses, sits at the top of this category as currently known. Each step up this ladder is not merely a quantitative increase. There are qualitative differences in how these objects form, how they interact with their environments, how they affect the galaxies they inhabit, and how we detect and measure them. TON 618 does not just sit at the extreme of a continuous distribution. It sits at the extreme where our models strain, and where the data forces us to confront the boundaries of our understanding. One of the most valuable aspects of objects like TON 618 from the perspective of cosmology rather than just black hole physics is what they reveal about the conditions of the early universe. The fact that TON 618's black hole reached 66 billion solar masses when the universe was only 3.3 billion years old tells us something about the abundance and properties of gas in the early cosmos. Building a black hole this massive requires enormous quantities of raw material gas that was available, dense enough to fall into the black hole's gravitational well, and not too turbulent or hot to be accreted efficiently. The early universe provided these conditions in a way the modern universe does not. Shortly after the Big Bang, within the first hundreds of millions of years, the universe was dominated by hydrogen and helium gas, with small seeds of dark matter halos around which ordinary matter accumulated gravitationally. These halos merged hierarchically, with small structures combining to form larger ones, and the gas they contained could cool and fall inward, building the first galaxies and feeding the first black holes. The conditions during this period, the cosmic dawn, were highly favorable for rapid black hole growth in ways that the diluted, star-filled, metal-enriched modern universe is not. TON 618's existence at redshift 2.219, corresponding to when the universe was about 3.3 billion years old, sits in the era when the universe's most vigorous black hole growth was occurring. The peak of quasar activity, also known as cosmic noon, spans roughly from about 2 to 4 billion years after the Big Bang, corresponding to redshifts between about 1.5 and 3. TON 618 falls squarely in that window, drawing from conditions of maximal availability that the universe would not sustain for much longer. Understanding those conditions, the gas supply, the dark matter halo structure, the rate at which matter could cool and fall inward, is central to understanding how the modern universe, with its quieter black holes and more sedate galaxies, emerged from the early universe's frenzy. TON 618 is, in a sense, a fossil of that early frenzy, captured in the light that has been traveling toward us for 10.4 billion years. Every measurement made of TON 618 is, simultaneously, a measurement of the universe as it was when very young, and a constraint on the models that try to explain how that young universe became the universe we live in now. The two questions are inseparable. The accretion disk is the workhorse of a quasar, the structure that converts gravitational potential energy into the electromagnetic radiation that we observe. And the efficiency of this process is startling even by the standards of astrophysics. Nuclear fusion in stars, the process that powers our Sun and every other star in the universe, converts approximately 0.7% of the mass of hydrogen fuel into energy via Einstein's famous E=mc² relationship. This 0.7% efficiency is, by any chemistry or conventional physics standard, remarkably high. The combustion of gasoline converts a fraction of a percent of the mass into energy. Nuclear fission in conventional reactors achieves about 0.1%. Fusion in the Sun achieves 0.7%. Accretion onto a black hole through the disk can achieve efficiencies as high as 40% for a maximally spinning black hole. Even for a non-rotating Schwarzschild black hole, the efficiency is about 6%, nearly 10 times better than nuclear fusion in stars. This means that for every kilogram of mass that falls into a quasar's accretion disk, up to 400 grams worth of energy can be released as radiation. That is an efficiency that makes every other energy conversion process in the universe look profligate by comparison. At TON 618's luminosity, 4 × 10⁻40 watts, and assuming an accretion efficiency in the typical range for active quasars, the black hole was consuming material at an extraordinary rate. Estimates for the accretion rate of a quasar at TON 618's luminosity place it at many solar masses per year, the equivalent of multiple suns' worth of mass falling into the accretion disk annually, being superheated, radiating their potential energy as electromagnetic radiation, and then crossing the event horizon. Year after year, for billions of years, that is how you build a 6 billion solar mass black hole. The temperature profile of the accretion disk ranges from millions of degrees Celsius in the innermost regions, close to the event horizon where the gas moves fastest and friction heats it most intensely, to cooler temperatures at larger radii where the gas is further from the center and moving more slowly. The innermost part of the disk, the region within about 3 times the Schwarzschild radius, called the innermost stable circular orbit, emits the hottest radiation, primarily X-rays and extreme ultraviolet. Further out, the disk cools to emit ultraviolet, optical, and finally infrared radiation. The integrated spectrum of a quasar accretion disk, the full distribution of radiation across all wavelengths, is called the Big Blue Bump, for the way the spectrum rises steeply through the ultraviolet before falling off in the blue bump. X-ray region. This spectral shape is one of the key identifiers of quasar accretion and is used to distinguish quasars from other types of high-energy sources. In TON 618's spectrum, this accretion disk signature is clearly present. Superimposed on the broad emission lines from the surrounding gas clouds, all of it redshifted from its emitted frequencies to what we observe in our instruments on Earth. Let the numbers fade for a moment. Let the equations dissolve. Picture the light leaving TON 618, not the blinding, searing accretion disk radiation, just the photons that happen to leave in our direction, aimed at a patch of sky that will someday contain Earth, though Earth does not exist yet when this light departs. The photons leave at the speed of light, as all photons do, and they begin their journey through a universe that is nothing like the one we inhabit. The universe around them is denser. There are no planets anywhere, or if there are, they are extremely rare, built from the first generation of stars that have just recently ended their lives and scattered the first heavy elements, carbon, oxygen, silicon, iron, into the interstellar gas. There are no oceans, no atmospheres with oxygen, no photosynthesis, no seasons. The universe is a younger, rawer place, its galaxies still assembling from the gas and dark matter that gravity has been collecting since the Big Bang. The photons travel. 1,000,000 years pass. The universe expands around them. They carry that expansion in their increasingly redshifted wavelengths. Their frequencies stretch lower. Their wavelengths grow longer. They are no longer quite the same photons that left the accretion disk. They carry the same information, but the universe has imprinted itself on them through the expansion. 1,000,000,000 years pass. Somewhere, in a quieter corner of the universe, the Milky Way is beginning to take shape, still assembling from its own mergers and gas infall. Sagittarius A star is growing at the center of that nascent galaxy, building toward its 4 million solar mass final mass. The photons from TON 618 are still traveling. 5 billion years pass. In a nondescript part of the Milky Way, a molecular cloud contracts under its own gravity, its center heating until it ignites nuclear fusion, and a new star appears our Sunday. A disk of gas and rock and ice swirls around it, and from that disk, gradually, slowly, a rocky planet coalesces at just the right distance to allow liquid water on its surface. The photons from TON 618 are still traveling. They have crossed more than half the distance now. The universe is expanding, carrying them forward, their wavelengths still stretching. 4.5 billion years pass. On that rocky planet, life has emerged, evolved, diversified into every ecological niche the planet offers. Insects evolve, then fish, then land animals, then reptiles, then mammals, then a lineage of mammals that begins using tools and language and eventually builds something called civilization. And within that civilization, something called science. And within science, something called astronomy. An observatory opens in the Mexican highlands. A catalogue is made. A number is assigned, 618. The photons arrive. They enter a telescope. They are dispersed by a spectrograph. A scientist looks at the spectrum and notices that the lines are shifted. She calculates the redshift. She determines the distance. She publishes the result. The universe's message, 10.4 billion years in transit, is received. The very long-term future of TON 618's black hole and black holes of its type throughout the universe is one of the stranger stories in cosmology, because it requires thinking about timescales so long that the word billion is not nearly enough, and where the familiar structures of the universe dissolve into something utterly alien. In the present universe, the universe of 13.8 billion years, black holes accumulate mass through accretion and mergers, but the universe is not static. The gas supply that fed the great quasar epoch has largely been converted into stars or dispersed. The rate of active feeding is declining everywhere. In the very long-term future, at timescales of tens or hundreds of trillions of years, the last stars will exhaust their nuclear fuel and die, leaving behind white dwarfs, neutron stars, and stellar black holes. The interstellar medium will thin further as residual gas continues to be consumed or ejected. At even longer timescales, roughly 10 to the power of 37 to 10 to the power of 100 years, protons may decay. If the proton lifetime permits it, white dwarfs will cool to black dwarfs, and the universe will consist primarily of the remnants of stellar death and the supermassive black holes sitting at the centers of galaxies, now dark and cold. These black holes, no longer fed by abundant gas, will dominate the mass budget of the universe in a way they currently do not. And then, over timescales measured by numbers that have no common name, 10 to the power of 100 years or more, Hawking radiation, that slow quantum evaporation of mass as energy, will gradually drain even the most massive black holes. TON 618's black hole, at 66 billion solar masses, has more mass to lose than almost any other object we know of, and correspondingly the longest Hawking evaporation time. But even that extraordinary lifetime has an end. What remains after the evaporation? Hawking's calculation, taken at face value, suggests that the final stages of evaporation become increasingly rapid as the black hole shrinks, ending in a burst of thermal radiation from a Planck mass remnant, or perhaps nothing at all, just a burst of energy and then silence. Whether information is preserved in that final burst, and in what form, connects back to the information paradox described earlier and has not been resolved. The universe, in that unimaginably distant future, will be cold, diffuse, and dark, a nearly featureless expanse of radiation and perhaps some exotic stable remnants, with no black holes, no stars, no galaxies, no planets. The monsters that dominated the early universe's most energetic period, objects like Ton 618, burning with 140 trillion solar luminosities, consuming solar masses annually, announcing their presence to the entire observable cosmos, will be gone. Their mass converted to radiation over timescales that dwarf the current age of the universe by factors that have no practical meaning to any mind of finite lifespan. In the fullness of the universe's own time, even the greatest thing we know of is temporary. If you want to point your eyes at the patch of sky where Ton 618 lies, not to see it, because it requires a substantial telescope and a very dark sky to observe, but simply to orient yourself toward it, the path is not complicated. Find the Big Dipper, which most people in the Northern Hemisphere can locate with relative ease. The Big Dipper's handle curves away from the bowl in a graceful arc. Follow that arc beyond the handle's end, continuing outward, and you will arrive at a bright orange-yellow star, Arcturus, one of the brightest stars in the northern sky. Part of the constellation Dwarf. Arcturus is the brightest star north of the celestial equator. Now look between the Big Dipper's bowl and Arcturus. That region of sky is occupied by Canes Venatici, the hunting dogs, a small, faint constellation with no bright stars, but some interesting deep sky objects for amateur astronomers. The Whirlpool Galaxy and the Sunflower Galaxy both lie in Canes Venatici, and the constellation was invented by the astronomer Johannes Hevelius in the 17th century, who imagined the pair of faint stars at its core as the hunting dogs held on a leash by the nearby constellation Boötes. Ton 618 lies in the direction of Canes Venatici, though not within the physical confines of any of its stars. Those stars are nearby objects in our own galaxy, lying between a few dozen and a few hundred light-years away. Ton 618 is 10.4 billion light-years behind them, in a direction that your line of sight passes through the foreground stars of Canes Venatici and then continues, past the Milky Way disk, past the local group of galaxies, past galaxy clusters and filaments of the cosmic web, through billions of light-years of expanding space, to the vicinity of a quasar burning in the early universe. On a sufficiently dark night, if you know where to look and have an adequate telescope, something in the range of a 1-2 inch or larger aperture, and the sky transparency is good, and you have a detailed finding chart from a star atlas, you can put the telescope on the right coordinates and capture, in the image, a faint point of light among thousands of other faint points. That point, if it is the right one, is the light that departed 10.4 billion years ago from one of the most extreme environments the universe has ever produced. You are not really seeing Ton 618. You are seeing its message, delivered across 10 billion years of space and time, waiting for you at the eyepiece of a telescope on a quiet night. The phrase in our title, mystery object, is not just rhetorical packaging. There is genuine mystery here, and it lives at multiple levels. At the first level, there is the mystery of what TON 618 is, a quasar, identified as such through careful spectroscopy, but still not fully understood in terms of its physical details. The geometry of the accretion disk, the structure of the jets, the detailed physics of the broad line region, the magnetic field configuration that drives the energy output. These are areas of active research where the observational constraints are still being refined and the theoretical models are still being tested. At the second level, there is the mystery of how Ton 618 got so massive so fast. The timing problem, building 66 billion solar masses in 3.3 billion years, does not have a fully satisfying resolution. and different proposed solutions carry different implications for early universe physics, seed black hole populations, and the relationship between dark matter structure and black hole growth. At the third level, there is the mystery of what TON 618 is now. We cannot see it as it currently exists. Whatever it became over the last 10 billion years is invisible to us. The black hole may have grown larger. The quasar may have shut down. The host galaxy may have merged with others. TON 618 might be the center of one of the largest galaxies in whatever galaxy cluster formed around it in the modern universe. Its black hole now dormant, but holding a mass that dwarfs anything we can measure nearby. At the fourth level, there is the mystery of whether there is something larger. TON 618 is the most massive black hole we have reliably measured. But reliably measured is a function of available technology, available observing time, and available targets. The universe contains 2 trillion galaxies, and we have measured the central black hole masses of a minuscule fraction of them. The record TON 618 holds may be broken the next time an astronomer turns a large telescope at a slightly different patch of distant sky. All of these mysteries are real. They are not manufactured for narrative effect. They represent the genuine state of knowledge at the research frontier, the place where observational astronomy, theoretical physics, and cosmology converge on objects so extreme that they strain every framework we have built to understand the universe. Mystery at the research frontier is not a failure of knowledge, it is the leading edge of it. The history of quasar research, from the confused early identifications of the 1950s to the sophisticated multi-wavelength campaigns of today, is one of the more satisfying stories in 20th and 21st century science. It has the character of all the best scientific detective stories, an anomaly that doesn't fit, a debate about what it means, a gradual convergence of evidence, and a resolution that turns out to reveal something more profound than the original puzzle. When Martin Schmidt published the spectral analysis of the quasar 3C 273 inches 1963, correctly identifying the extreme redshift and placing the object at a cosmological distance, the response from the astronomical community was not unanimous celebration. Some prominent astronomers resisted the cosmological interpretation for years, arguing that local mechanisms could explain the large redshifts without invoking distances of billions of light-years. The discomfort was understandable. If quasars really were at cosmological distances, their luminosities were so extreme as to be physically implausible by the physics of the day. The energy output required was greater than any known mechanism could produce. What resolved the debate, ultimately, was not a single piece of evidence, but the accumulation of many independent lines. The correlation of quasar number density with redshift, showing that quasars became rarer in the lower redshift, more recent universe was difficult to explain except through cosmological distance. The statistical distribution of quasar properties with redshift, consistent with standard cosmological models and inconsistent with local ejection models. The development of the black hole accretion paradigm, which provided a physical mechanism mass falling into a deep gravitational well capable of producing the required luminosities, and eventually, the imaging of quasar host galaxies with the Hubble Space Telescope, showing that quasars sit at the centers of galaxies at the distances their redshifts implied. Margaret Burbidge, who identified TON 618 as a quasar in 1970, was a central figure in this broader history. She and her husband, Geoffrey Burbidge, along with William Fowler and Fred Hoyle, had co-authored the landmark 1957 paper known as B²FH, for the author's initials that worked out how the elements heavier than hydrogen and helium were synthesized in stars. It is one of the foundational papers of 20th century astrophysics. Burbidge's work on quasars, including her identification of TON 618, added another chapter to a scientific career of extraordinary breadth and impact. The quasar research that Burbidge and others conducted in the 1960s and 1970s built the intellectual foundation that allows us today to discuss objects like TON 618 with a degree of confidence and understanding that would have been impossible in the decade after Schmidt's landmark paper. The methods, the debates, the hard-won insights, all of it is baked into the context within which TON 618's story makes sense. A question that sometimes arises when discussing objects at this scale is whether it matters. TON 618 is 10.4 billion light-years away. It cannot affect us. Its radiation cannot reach us in any dangerous way. The inverse square law of radiation intensity, combined with the expansion of the universe, means that TON 618's light arrives at Earth already enormously diluted, faint enough to be measured only by powerful telescopes. Its gravity, while enormous in the vicinity of the black hole itself, exerts no measurable influence on anything outside its host galaxy. It is not a threat. It is not a resource. It is not accessible to us in any practical sense in any time frame that connects to human concerns. So why care? The answer, which is not really an argument but more of an observation about human nature, is that caring about the extreme and the distant is one of the things that makes science what it is. The instinct to understand, not just to know facts, but to comprehend the structure of things, to map the boundaries of what exists and how it works, is not instrumentally motivated. It does not produce immediate practical returns. The fundamental research that revealed quasars and measured TON 618's mass did not put food on any table or cure any disease in a direct sense. But that same instinct, pursued in other directions, produced the physics of electromagnetism that underlies all of modern communication technology. It produced the quantum mechanics that underlies transistors, lasers, and medical imaging. It produced the general relativity that underlies the GPS systems that navigational applications run on. The knowledge built up at the frontier of pure science, at objects like TON 618 where the physics is extreme and poorly understood, has a history of eventually finding its way back into the practical world in forms that were entirely unpredictable at the time of discovery. More immediately, there is something that people describe as perspective. Not in the cheap sense of our problems are small compared to the universe, that observation, while technically true, is not particularly useful emotionally, but in the sense that the universe is vastly larger, older, and more complex than our daily experience suggests, and knowing something about its extremes, its most massive black holes, its most energetic phenomena, its deepest past, gives the mind a framework that is simply absent without it. You navigate through a richer mental landscape if you know, at some level, that there is an object 10.4 billion light-years away whose black hole outweighs 66 billion suns, whose light has been traveling since before the Earth formed, and whose existence we inferred from spectral lines measured with instruments built on a rocky planet that the universe didn't produce until 7 billion years after the light left. Whether that enriches your daily life is personal, but it is not nothing. We started with a claim that TON 618 is the most terrifying object in the known universe, and that it is not technically a black hole. Both parts of that claim deserve their final accounting. The technical distinction, TON 618, is a quasar, which means it is an actively feeding black hole. The distinction matters because, as we have explored, a feeding black hole, a quasar, is qualitatively different from a dormant black hole in ways that make it more immediately consequential for the space around it. The radiation, the jets, the energetic winds, the environmental effects on surrounding gas and star formation, all of these make a quasar something more than just a very massive black hole. It is a black hole that is doing something, and what it does makes its surroundings inhospitable across distances that a dormant black hole could never threaten. The terror claim, this is more subjective, but the numbers support it as well as numbers can support an emotional assessment. A black hole of 66 billion solar masses, operating at 140 trillion solar luminosities, at the age of the universe when such extremes were more common, producing jets of relativistic plasma across possibly millions of light-years. There is no object in any catalogue of known phenomena that combines these characteristics at greater magnitude. TON 618 is, on the metrics of mass and luminosity that make an object astrophysically extreme, the exemplar of its class. What the monster left us, aside from the spectral lines that revealed its presence, is a set of questions. How did it grow so fast? The universe does not seem to have had time, under standard models, to build something that massive in 3.3 billion years, and yet it did. That discrepancy is an invitation to improve the models. What is it now? The universe has continued for 10.4 billion more years since the light we see departed, and TON 618's current state is unknown to us. That inaccessibility is a reminder of the limits of observation we see. The past and the present remains beyond reach until the light arrives. Is there something larger? The observable universe contains 2 trillion galaxies. TON 618 holds the mass record among objects we have measured. Whether it holds the mass record among objects that exist is a different question entirely, and one that future telescopes may begin to answer. What happens inside? The singularity at TON 618's core, and at the core of every black hole, is the point where our physical theories break down and the universe knows something we do not. That boundary is one of the most honest statements physics can make about itself. Here is what we know, and here is where we stop knowing. And the universe continues on the other side of that line without asking our permission. The light that left TON 618 10.5 billion years ago and travelled across the expanding universe to reach our instruments on Earth tells us all of this. It tells us through the wavelengths it has been stretched to, the broad lines imprinted in it by orbiting gas, the luminosity we can calculate from its apparent brightness and its known distance. It tells us everything it can tell us, and then it stops, because a photon carries only so much information, and the universe behind it has moved on. TON 618 is a snapshot of a fire that burned hotter than anything else we can observe. Whether that fire is still burning, whether it went dark, whether something larger has taken its place, those are stories the universe is still writing in light that has not yet arrived. We will wait. We will build better instruments. We will ask better questions. The universe, patient and indifferent, and staggeringly large, will keep sending us its messages, one photon at a time, across distances that take billions of years to cross, from events that happened before Earth existed, from objects that may no longer exist as we see them, and we will keep listening. General Relativity, Albert Einstein's masterwork, published in 1915, rewrote the way physicists understand gravity by describing it not as a force pulling objects toward one another, the way Newton described it in 1687, but as the curvature of space-time caused by mass and energy. In Einstein's framework, massive objects warp the four-dimensional fabric of space-time around them, and other objects, including light itself, follow the straightest possible paths through that warped geometry. What looks like gravitational attraction is, at the deepest level, the geometry of space-time guiding objects along the paths that curved space makes available to them. This shift in perspective from Newton to Einstein has practical consequences. Newton's gravity works superbly well for everyday astrophysics, calculating planetary orbits, predicting the trajectories of spacecraft, modeling the dynamics of stars in a galaxy, but it fails in regimes of extreme gravity, where space-time curvature becomes so pronounced that Newton's approximation diverges significantly from reality. The vicinity of a black hole is precisely such a regime, where the curvature becomes so extreme that it dictates not just the paths of particles, but the structure of time itself. Near a massive object, time runs more slowly than it does far from that object. This is not a metaphor or an approximation, it is a physical reality that GPS satellites have to account for in their timing systems, and that atomic clocks transported to different altitudes have measured directly. Clocks closer to a massive object tick more slowly than clocks far away from it. As you approach a black hole's event horizon, this effect, called gravitational time dilation, becomes increasingly severe. At the event horizon itself, time dilation becomes infinite. A clock at the horizon would, from the perspective of a distant observer, appear to stop completely. For TON 618's black hole, with its enormous event horizon at 1,300 astronomical units radius, the gravitational time dilation gradient across human scales at the horizon is relatively gentle because the horizon is so far from the singularity that the gradient in gravitational potential across a human body is not steep. The time dilation at the horizon is still formally infinite, an infinite factor applied to any finite tick rate, but the tidal variation across a person-sized object is mild, consistent with the earlier observation that crossing this particular horizon would not immediately feel extreme from the infaller's perspective. The geodesics, the paths that free-falling objects follow through curved spacetime around TON 618's black hole, describe an extraordinary geometry. At the photon sphere, roughly 1.5 times the Schwarzschild radius from the center, photons can orbit in unstable circular paths. An observer at the photon sphere looking sideways would see the back of their own head. Looking in any direction, they would see light from every other point on the photon sphere, creating a complete closed-loop image of the entire sphere visible in every direction. This is not an illusion or an analogy, it is what the geometry of spacetime at that radius produces. The bending of light around the black hole is complete enough, at that radius, to form closed circular paths. Inside the photon sphere, toward the event horizon, the bending of light becomes even more extreme. The solid angle of sky visible to an infalling observer, the fraction of directions from which light can arrive, shrinks as the observer approaches the horizon. At the event horizon itself, the entire outside universe appears compressed into a single bright circle directly above, in the direction of motion toward the singularity, an effect called the relativistic photon cone, or the aberration of light in strong fields. Rotating black holes, which are described by the Kerr metric rather than the Schwarzschild metric, add another layer of complexity. A rotating black hole drags spacetime around with it in a phenomenon called frame dragging, creating a region outside the event horizon called the ergosphere, where spacetime itself is dragged in the direction of rotation faster than the speed of light relative to distant observers. Within the ergosphere, it is impossible to remain stationary relative to distant stars. All objects, including light, are swept around in the direction of the black hole's spin. This region can, in principle, be tapped for energy through a process called the Penrose process, in which an object splits inside the ergosphere and one fragment is captured, while the other escapes with more energy than it entered, with extracting energy from the black hole's rotation. TON 618's black hole is almost certainly rotating. Astrophysicists expect all black holes to carry angular momentum, both from the spin of the material that formed them and from the ongoing infall of material through the accretion disk. The spin of a black hole, measured on a scale from 0 non-rotating Schwarzschild to 1 maximally rotating Kerr, affects the innermost stable circular orbit of the accretion disk, and therefore the efficiency of energy extraction. A maximally rotating black hole allows accretion disk material to orbit much closer to the event horizon, where the gravitational potential is deeper, extracting up to 42% of the rest mass energy of the infalling material, compared to the 6% possible for a non-rotating black hole. The spin of TON 618's black hole has not been precisely measured from the available data, but its luminosity relative to its mass provides constraints on how efficiently it was converting mass to energy during the era of peak activity, we observe. TON 618 does not exist in isolation. No galaxy and no quasar exists in isolation. The universe is structured at the largest scales into a network of filaments and sheets of dark matter and gas, punctuated by dense nodes where galaxies and galaxy clusters accumulate, surrounding vast empty regions called cosmic voids. This cosmic web, as it is called, was seeded by tiny quantum fluctuations in the density of the very early universe, amplified by gravity over billions of years into the elaborate structure we observe today. At a redshift of 2.219, TON 618 existed in a universe whose cosmic web was already well developed, but still considerably more compact and active than the modern web. Galaxy clusters at that epoch were still assembling, merging, and accreting material from the surrounding filaments, and the density contrast between the overdense nodes and the underdense voids was still increasing as gravity continued to amplify the initial fluctuations. Massive quasars like TON 618 preferentially inhabit the densest nodes of the cosmic web, the regions where dark matter halos are most massive, where gas supplies are most abundant, and where the environmental conditions most favor rapid black hole growth. A quasar of TON 618's luminosity almost certainly sat at the center of a massive dark matter halo, a region perhaps hundreds or thousands of times denser than the cosmic average, hosting a galaxy or protogalaxy of substantial mass and feeding the central black hole from the reservoir of gas falling in along the filaments of the cosmic web that connected it to the surrounding large-scale structure. The environment around such a massive quasar would have been unusual in other ways. Massive black holes and the galaxies hosting them have followers, smaller galaxies that cluster around the massive central galaxy, drawn in by the gravitational potential of the dark matter halo. The space around TON 618's host galaxy was almost certainly populated with satellite galaxies, some of them being stripped of their gas and stars by the tidal forces of the central galaxy, others falling inward to eventually merge with it. These mergers, in turn, can supply fresh gas to the central black hole, fueling the quasar activity for additional periods. The interplay between the large-scale cosmic web, the galaxy population it contains, the gas flows it channels, and the black holes growing at the centers of massive halos is one of the central problems in cosmological simulation. Modern cosmological simulations, computational models of the universe that evolve billions of dark matter particles, gas particles, and star particles from the Big Bang to the present day, have made remarkable progress in reproducing the large-scale structure of the universe, the statistical properties of the galaxy population, and the growth of central black holes. But the most extreme objects, quasars, at TON 618's luminosity and mass remain challenging to reproduce exactly, partly because the relevant physics spans an enormous range of scales from subparsec accretion disk dynamics to megaparsec cosmic web structure, and no simulation can simultaneously resolve all of them. Modern quasar research is inherently multi-wavelength. No single region of the electromagnetic spectrum captures the full picture of what a quasar is doing, because different physical processes in different parts of the quasar structure emit radiation at different wavelengths. Understanding TON 618 as completely as the data allows requires integrating observations from radio waves through X-rays and potentially including gravitational wave signals in the future. Radio observations of quasars reveal the jets. The relativistic plasma jets launched from the poles of the central black hole, accelerated by magnetic fields, threading the accretion disk and anchored in the rotating spacetime of the black hole's ergosphere, emit radio waves through a process called synchrotron radiation, in which electrons spiraling around magnetic field lines radiate at frequencies that depend on their energies and the strength of the magnetic field. Radio observations can trace the structure of quasar jets on scales ranging from parsecs to megaparsecs, revealing the jets' morphology, their speeds, and the way they interact with and heat the gas in the galaxy and in the surrounding galaxy cluster. Infrared observations trace the cooler material in the quasar system, the dust that surrounds the accretion disk and the broad line region, absorbing the ultraviolet radiation from the disk and re-radiating it at longer infrared wavelengths. The infrared emission from quasars encodes information about the amount and distribution of dust, the temperature structure of the surrounding environment, and the star formation rates in the host galaxy, which can be estimated from the ratio of infrared to ultraviolet emission. Optical and ultraviolet observations capture the accretion disk's direct radiation and the emission lines from the broad line region and the narrow line region, the two zones of ionized gas surrounding the quasar at different distances. The broad line region, as discussed, provides the mass measurement. The narrow line region, at larger distances and lower velocities, provides information about the larger scale ionization environment and the way the quasar's radiation affects the surrounding galaxy. X-ray observations probe the innermost, hottest regions of the accretion disk and the corona, a region of hot plasma above the disk, from which X-rays are produced through inverse Compton scattering, a process in which electrons transfer energy to photons, boosting them to X-ray energies. X-ray spectra contain an enormous amount of information about the conditions near the event horizon, including signatures of ion emission lines that are relativistically broadened and skewed by the extreme gravity near the innermost stable circular orbit, potentially allowing the spin of the black hole to be constrained from the shape of those lines. For TON 618, at a distance of 10.4 billion light-years, the observational challenges are formidable. The signal is faint after traveling so far through expanding space. The redshift moves the emitted wavelengths into different observed bands. What was emitted as ultraviolet arrives at optical wavelengths, and what was emitted at X-ray energies arrives at lower X-ray or ultraviolet energies, calibrating the measurements, understanding the uncertainties, and building a coherent physical model from multi-wavelength observations requires sophisticated analysis and careful attention to the ways that observational selection effects might bias the apparent properties of the object. Despite these challenges, TON 618 has been observed across multiple wavelength ranges by instruments in space and on the ground. Its redshift, its spectral characteristics, its broad emission lines, and its apparent brightness in various bands have all been measured with sufficient precision to support the physical characterization, the mass, the luminosity, the cosmological distance that makes it one of the most precisely characterized of the most extreme quasars known. There is an aspect of TON 618's environment that has not yet been addressed, but that is central to understanding how a structure as extreme as this quasar formed: the role of dark matter. Dark matter, matter that interacts gravitationally but does not emit, absorb, or scatter. Electromagnetic radiation accounts for roughly 27% of the universe's energy density, compared to about 5% for ordinary matter, the matter that makes up stars, planets, gas, dust, and everything you can directly observe. Dark matter does not form stars or planets. It does not radiate. It cannot be seen directly. Its existence is inferred from its gravitational effects, the way galaxies rotate, the way galaxy clusters bend light from background objects through gravitational lensing. The large-scale structure of the cosmic web and its identity at the particle physics level remains one of the deepest unsolved problems in physics. Dark matter is nevertheless the dominant player in structure formation. In the early universe, quantum fluctuations in the density of dark matter, tiny overdensities and underdensities that existed from the moment of inflation, the period of exponential expansion that is believed to have occurred a tiny fraction of a second after the Big Bang, provided the gravitational seeds around which ordinary matter accumulated. Dark matter halos, gravitationally bound clumps of dark matter assembled hierarchically, from small halos forming early to larger halos assembling through mergers, and the ordinary matter, gas, that fell into these halos cooled, condensed, and formed the first galaxies and the first black holes. For a quasar like TON 618 to reach its observed mass and luminosity by 3.3 billion years after the Big Bang, the dark matter halo in which it formed would have had to be among the most massive halos present in the universe at that epoch. Massive dark matter halos assemble earlier in the high-density regions of the universe. The future sites of today's most massive galaxy clusters and the quasar activity associated with them is correspondingly vigorous and early. The most extreme quasars observed at high redshifts, including TON 618, are believed to inhabit the most extreme dark matter overdensities of their era, the peaks of the cosmic density field. This connection between dark matter structure and quasar activity is one of the threads that tie together two seemingly different areas of physics, particle physics and cosmology, on the dark matter side, and black hole physics and galaxy evolution on the quasar side, into a single coherent picture of how the universe built its most extreme structures. We cannot observe TON 618's dark matter halo directly, any more than we can observe dark matter anywhere. But we can infer its properties from the quasar's characteristics, from the expected relationship between halo mass and black hole mass, and from simulations of structure formation that model both the dark matter and the ordinary matter evolution together. The dark matter halo surrounding TON 618's host galaxy at the time of observation was almost certainly among the most massive present in the universe. At redshift 2.219, a halo of perhaps hundreds of billions to trillions of solar masses, providing the gravitational potential that held the host galaxy together, channeled gas inflows from the cosmic web, and governed the environmental conditions in which the central black hole grew. That invisible scaffolding, the dark matter halo, is in some sense more fundamental to the story of TON 618 than any of the luminous structures we can directly observe. There is value in pausing to imagine, even imprecisely, the kind of moment that science produces when a discovery of this magnitude comes together from the data. Margaret Burbidge was not a young astronomer in 1970 when the identification of TON 618 as a quasar was established. Born in 1919 inches Davenport, England, she had by that point built one of the most distinguished careers in astrophysics of the 20th century. The B-squared FH paper on stellar nucleosynthesis, still cited extensively today, was behind her. She had spent years studying the spectra of galaxies and active galactic nuclei, developing expertise in the spectral signatures that revealed the physical conditions of distant objects. The identification of a new quasar was not, for someone of her experience, a shocking revelation. It was the careful reading of a spectrum, the recognition of a pattern, the application of well-understood principles to a new example. And yet there is something in the moment of recognition that no amount of experience can make entirely routine. The spectral lines shifted to their cosmological redshift, the calculation of how far away the source must be, the recognition that the brightness implies a luminosity that numbers can barely capture. These are the moments when the data transcends the data and becomes something else, a window. A photograph of the universe as it was when the light departed, in this case, when the universe was not yet 4 billion years old. The tools available in 1970 were not what we have today. The spectrographs were photographic rather than digital. The data reduction was done by hand or with analog computing equipment rather than automated processing pipelines. The analysis was slower and more labor-intensive than any modern astronomer would recognize. And yet the physics encoded in the spectral lines is the same physics. The redshift is the same redshift. The distance is the same distance. The measurement was real. The discovery was real. What Burbidge and her collaborators established from their instruments on those observation nights was that a catalogue entry from a Mexican observatory filed as a blue star in 1957 was something far stranger and far more distant than any star, a glimpse back 10.4 billion years in time to a burning, ultramassive engine that the universe had constructed in its youth and that no star could approach in terms of energy output. The work of science, conducted by people in observatories on quiet nights, with equipment built by human hands, informed by theory developed by human minds, connected by correspondence and conferences, and disagreement and refinement, produced this knowledge. The universe did not volunteer the information. It had to be extracted, piece by piece, from light that was already ancient when the observatory opened. One of the tools that astronomers use to study very distant, very faint objects is gravitational lensing, the bending of light by massive objects lying between us and the source. General relativity predicts that any mass will bend the path of light passing near it, just as a glass lens bends light through refraction. A galaxy or galaxy cluster lying along the line of sight to a more distant object can act as a natural gravitational lens, bending the light from the background source and producing multiple images, arcs, or rings that are brighter and larger in apparent size than the unlensed source would be. Gravitational lensing is routinely used to study very high redshift galaxies and quasars that would otherwise be too faint to study in detail. Hubble Space Telescope observations of galaxy clusters have produced iconic images of gravitationally lensed arcs, the distorted, magnified images of galaxies lying billions of light-years behind the cluster, their light bent around the cluster's mass distribution into curved arcs of blue-white or gold-orange light. For the study of distant quasars like those in TON 618's class, gravitational lensing can be both a tool and a complication. A lensed quasar appears brighter than it would otherwise, making it detectable at greater distances and allowing spectral studies that would be impossible without the magnification. But lensing also changes the apparent brightness, which must be carefully accounted for when using brightness to infer luminosity, and can produce multiple images that are separated by tiny angles on the sky, potentially being mistaken for a single source without sufficiently high-resolution imaging. For TON 618 specifically, the question of whether a significant lensing magnification contributes to its apparent brightness has been considered in the analysis of its properties. If the brightness that we observe includes a substantial lensing boost, the true luminosity, and therefore the inferred mass from virial methods, would need to be revised. The analysis that established TON 618's properties accounts for these possibilities, and the consensus from the available data places TON 618's luminosity and mass at the values cited throughout this discussion. But the ongoing refinement of such measurements as better instruments become available is exactly the kind of work that keeps the observational characterization of extreme quasars an active research area. The universe's gravitational lensing machinery, in a broader sense, is part of what makes astronomy at TON 618's distances possible at all. Without the natural telescopes provided by intervening mass concentrations, the very faintest and most distant objects would remain essentially unobservable. The cosmic web of dark matter and galaxies is, inadvertently, an optical system, a complex, irregular, but occasionally useful array of natural magnifiers that allow us to see further than our instruments alone would permit. Let's be honest about something that comes up when people genuinely sit with the numbers associated with objects like TON 618, rather than passing through them quickly as items on a fact list. There is a characteristic response that many people report when they really try to absorb what 10 billion light-years of distance means, or what 66 billion solar masses represents, or what it implies to be looking at light that departed before the Earth formed. The response is not quite fear, though fear is an element of it. It is closer to a kind of vertigo, a cognitive step that the mind begins and cannot complete, because the number or the scale or the time frame exceeds the framework that ordinary experience built. Psychologists sometimes refer to the emotion evoked by experiences of vast scale, overwhelming complexity, or something that dwarfs ordinary human frames of reference as awe. It is characterized by a sense of the smallness of the self relative to the thing perceived, often combined with a sense of the thing's significance, a feeling that you are in the presence of something that matters in ways that transcend immediate concerns. Research on awe suggests that it tends to produce increased feelings of connectedness, reduced preoccupation with personal concerns, and increased curiosity about the world effects that are, whatever their evolutionary origin, broadly valuable. TON 618 is an effective producer of awe for those who let the numbers land. The event horizon that light takes 22 days to cross, the luminosity of 140 trillion suns, The 10.4 billion year journey of the light that tells us all of this. Each of these numbers, followed honestly to its implications rather than skimmed past, opens a little window onto a scale that the ordinary mind cannot house but reaches toward anyway. There is a tradition in astronomy of describing this response as one of the gifts that the study of the universe provides. Carl Sagan wrote about it with characteristic eloquence. Neil deGrasse Tyson has spoken about it in countless public venues. But the response does not require eloquence to be real. It is available to anyone who pauses long enough with the numbers to let them do their work. The universe arranged Ton 618 into existence 10.4 billion years ago, and it arranged, through the subsequent 10.4 billion years of cosmic and biological and cultural and technological evolution, the conditions under which a species on a small rocky planet could build instruments to detect the light, write equations to analyze it, and sit with the results in a state of genuine astonishment. That chain of events is, itself, worth a moment of attention. The discovery of quasars was inextricably linked to the development of radio astronomy in the mid-20th century. Before radio telescopes, astronomy was entirely optical. You needed light that human eyes or photographic emulsions could detect. The introduction of radio wave detection into astronomy opened a completely new window on the universe, revealing objects and processes invisible to optical instruments. The first radio surveys of the sky in the 1950s, conducted with large radio antennas in Britain, Australia, and the United States, catalogued hundreds of radio sources designations like 3C for Third Cambridge Catalogue, followed by a number. Many of these radio sources, when astronomers tried to identify their optical counterparts, turned out to correspond to nothing particularly unusual radio galaxies, supernovae remnants, known nebulae, but a subset of them seemed to correspond to faint, point-like optical sources that looked like stars but had no reasonable stellar explanation for their radio emission. When spectra of these point-like sources were taken, the large redshifts revealed their cosmological distances and their extraordinary luminosities. The term quasi-stellar radio source was coined because these objects looked like stars but were not. Most quasars, it turned out, are not strong radio emitters. The fraction of quasars that are radio loud is roughly 10%, with the remainder being radio quiet, though not radio silent. TON 618 was not identified as a quasar through radio emission, but through its spectral characteristics, its large redshift. The TON designation connects it to the optical survey at Tonantzintla, not to a radio catalogue. The expansion of quasar samples from the initial radio-selected objects to optically selected, X-ray selected, and eventually infrared-selected samples has revealed that quasars are far more numerous than the early radio surveys suggested, simply because the majority of them do not produce the copious radio emission that the initial discoveries required. Modern quasar surveys, using digital sky surveys that scan millions of square degrees with sensitive optical detectors, have identified hundreds of thousands of quasars at a wide range of redshifts, luminosities, and spectral properties. Ton 618 stands out from this large population, not because of any rare physical mechanism. It is a quasar, like other quasars, obeying the same physics, but because of the extreme values of its mass and luminosity, which place it at the very top of the distribution. The history of radio astronomy and quasar discovery is also deeply intertwined with the development of interferometry, the technique of combining signals from widely separated radio antennas to achieve angular resolution far beyond what any single antenna can provide. Very long baseline interferometry, or VLBI, uses antennas spread across entire continents or even the full diameter of the Earth to achieve angular resolutions measured in micro-arcseconds, allowing the detailed imaging of structures at the cores of distant active galaxies with extraordinary precision. The Event Horizon Telescope, which produced the first images of a black hole shadow for M87 in 2019 and for Sagittarius A* in 2022, is a form of VLBI pushed to its ultimate limit. For TON 618, at 10.4 billion light-years, the angular scales that VLBI would need to resolve the innermost structure of the accretion disk are far beyond even the Event Horizon Telescope's capability. The physical size of the accretion disk's innermost region subtends an angle on the sky so tiny that it would require a baseline comparable to the Earth-Moon distance or larger to resolve. Future space-based VLBI missions, with antennas deployed at large distances from Earth, might someday begin to probe these scales for objects closer than TON 618, and the knowledge gained could be extrapolated to improve our physical models of the most extreme quasars. The relativistic jets produced by actively feeding black holes deserve considerably more attention than they typically receive in discussions of individual quasars, because they represent one of the most energetic and poorly understood phenomena in all of astrophysics. A relativistic jet is a collimated stream of plasma electrons, positrons, and possibly protons launched perpendicular to the accretion disk plane and accelerated to velocities very close to the speed of light. The mechanism by which these jets are launched, collimated, and maintained over distances of millions of light-years is not fully understood, though the leading theoretical framework involves the extraction of rotational energy from the spinning black hole, the Blandford's-Nayak mechanism, or from the rotating inner accretion disk, the Blandford-Payne mechanism, through large-scale magnetic fields. The synchrotron radiation produced by the relativistic electrons spiraling in the jet's magnetic field spans from radio waves through X-rays, and the jets can also produce very high-energy gamma rays through inverse Compton scattering. For some jet-powered sources called blazars, quasars whose jets are pointed nearly directly toward Earth, the beamed radiation from the jet dominates the observed emission across all wavelengths, boosted in apparent luminosity by the relativistic Doppler effect of the jet moving toward us at nearly the speed of light. The jets of massive quasars like those in TON 618's luminosity range carry enormous quantities of energy into the surrounding galaxy and galaxy cluster. The interaction of jet plasma with the surrounding gas, the hot, diffuse medium that permeates galaxy clusters and fills the space between galaxies within them, produces enormous cavities, shock waves, and ripples that heat the gas and prevent it from cooling to form new stars. This is a different manifestation of AGN feedback from the radiation-driven variety, mechanical feedback, deposited by the physical excavation and heating of gas by the jet. Both mechanisms, separately and in combination, contribute to the regulation of star formation in massive galaxies. Observations of nearby galaxy clusters have revealed spectacular examples of jet-powered cavities, enormous bubbles of radio-emitting plasma inflated by jets into the hot cluster gas, displacing vast volumes of material and heating the surrounding medium. The Perseus cluster, the Centaurus cluster, and numerous others show these structures clearly in X-ray images taken by the Chandra X-ray Observatory, revealing the mechanical energy deposited by jets into the cluster environment over billions of years. For TON 618, at its observed luminosity, the jets, if present and at a typical power fraction of the total luminosity, would carry energies that dwarf anything observed in nearby objects. The jets of TON 618, class quasars during the peak activity era of the universe, may have played a significant role in shaping not just their host galaxies, but the surrounding galaxy clusters and even the cosmic web on scales of millions of light-years. The hot, X-ray emitting gas that fills galaxy clusters today carries the thermal memory of this early jet, heating a fossil record of the mechanical energy deposited by the most powerful jets in the early universe. Understanding this jet feedback, quantifying it, and incorporating it into cosmological models of galaxy and cluster evolution is one of the central challenges of observational and theoretical astrophysics. TON 618, as an extreme representative of the jet-powered quasar population, is both a compelling individual case study and a benchmark against which models of jet feedback must be tested. This is not a section about the existence of alien civilizations, a subject that this script cannot resolve, but rather a thought experiment about the observational environment in the vicinity of TON 618 during its active phase. Consider a hypothetical planet orbiting a star at a distance of, say, 1,000 light-years from the center of TON 618's host galaxy. 1,000 light-years is enormous by the standard of our solar system's environment, but a small distance by galactic standards comparable to the distance from our Sun to some of the more distant star-forming regions in our part of the Milky Way. The sky for inhabitants of that hypothetical planet would not look like our sky. In our sky, the Milky Way appears as a faint band of diffuse light, the combined glow of hundreds of billions of stars seen edge on from within the disk. The brightest individual objects are nearby stars, the Moon, and the planets. The total night sky is relatively dim. From a planet 1,000 light-years from TON 618's center, the quasar would be by far the dominant object in the sky. At that distance, 1,000 light-years, or approximately 9.46 times 10 to the power of 15 kilometers, the quasar's luminosity of 4 times 10 to the 40th watts, reduced by the inverse square law, would still produce an irradiance enormously exceeding what our Sun produces at Earth. The quasar would not just be a bright point in the sky, it would be a source of radiation intense enough to dominate the energy environment of the planet far more completely than our Sun dominates Earth. The radiation at that distance would not be in the form of visible light from an accretion disk that looks like the Sun. It would be primarily ultraviolet and X-ray radiation from the hot inner disk, along with the radio and gamma-ray emission from jets if the planet happened to lie near the jet axis. Shielding from this radiation would require either a thick, chemically rich atmosphere with strong ultraviolet blocking properties, or a naturally magnetospheric planetary environment capable of deflecting the high-energy charged particles. The surface conditions would be, by any biology we understand, extremely hostile. At 10,000 light-years from the quasar, comparable to the distance from the Sun to the galactic center in our own galaxy, the irradiance would drop by a factor of 100 relative to the 1,000 light-year case, making conditions significantly more moderate. The quasar would still dominate the visual sky, appearing as an extraordinarily luminous point with a visible nucleus and possibly visible jet structures extending from it across a substantial fraction of the angular sky. The hard radiation at this distance would be at levels that, depending on the atmospheric properties of a planet and its distance from its own star, might be compatible with the survival of simple life forms, though still far more intense than what any life on Earth has ever experienced. At 100,000 light-years approaching the scale of the host galaxy's full-extent conditions become substantially more Earth-like in terms of the quasar's radiation contribution to the environment. The quasar's contribution to the sky's radiation background, while still measurable and significant, begins to fall below the threshold where it is necessarily incompatible with biological chemistry of the types we know. The galaxy's own stellar population, hundreds of billions of stars, many of them hosting planetary systems, would provide environments where, in principle, the conditions for biology might be satisfied. This thought experiment illustrates why the active quasar era of the early universe is generally considered inhospitable to life as we understand it. Not because life is impossible anywhere in a universe containing active quasars, but because the most favorable habitable zones, well away from the quasar's radiation field, are more limited, and the overall cosmic environment is simply more energetically hostile than the quieter universe of today. We live in what might be called the habitable epoch of the universe, when the most violently energetic phenomena have largely shut down, the stars are burning steadily, and the long-lived, low-mass stars that are most favorable for planetary habitability are in their prime. There is a philosophical dimension to the study of objects like TON 618 that occasionally surfaces in public discussions of astronomy but rarely gets the sustained attention it deserves. It has to do with the relationship between the scales of the universe and the meaning of the human experience within it. The standard response to the immensity of the universe, the response that can feel dismissive, even when it is well-intentioned, is some version of "we are very small and the universe is very large." This is true but insufficient, because it treats size and significance as synonyms, which they are not. A bacterium is orders of magnitude smaller than a human being, but that smallness does not bear on the bacterium's importance to the ecosystem it inhabits or the biological processes it carries out. Size is one dimension of reality. Significance, to the extent it is a meaningful concept at all, seems to operate on different axes. What the study of TON 618 and objects like it actually illustrates, philosophically, is less about the smallness of humanity and more about the remarkable fact that the universe, which did not design itself with human minds in mind, which operated for 10.4 billion years before the light carrying TON 618's information reached Earth, which contains 2 trillion galaxies, mostly uninhabited by anything that can look at them, produced in at least one location, a kind of matter capable of modeling the universe's own history. Minds that can reconstruct, from spectral line widths and luminosity measurements and relativistic equations, the mass of a black hole that formed billions of years before those minds existed. That is not a small thing. It is perhaps the most remarkable thing that can be said about the universe, that it produced, somewhere in its vast architecture, the capacity for self-knowledge. Whether that self-knowledge is ultimately meaningful in a deeper sense, whether the universe's knowing itself through conscious beings constitutes something important, is a question that physics cannot answer, and philosophy has not settled. But the fact of it is undeniable. The universe generated beings who can look outward 10.4 billion light-years, inward through 10.4 billion years of history, and recognize what they are looking at. TON 618, in this light, is not just a record-holding black hole. It is one of the data points that the universe has provided for its own contemplation, received and processed by beings whose existence is improbable, whose knowledge is partial, and whose curiosity appears, against all evolutionary expectation, to be genuinely boundless. When you come back to the beginning of this story, the quiet observatory in Mexico, the photographic plates, the catalogue entry, the faint blue star that was not a star, and you follow the thread all the way through to the 6 billion solar mass black hole, the 140 trillion solar luminosity, the 10.4 billion light-year distance, the unsolved problems of its growth and its current state, and what lies inside its event horizon, you arrive somewhere that is difficult to name precisely. It is not comfort. The universe that contains TON 618 is not a comfortable place by any definition that privileges biological survival and earthly scale. It is not despair either, because despair would require the expectation of a different outcome, and the universe never promised anything else. It is something more like recognition, the specific quality of attention that comes from looking at a thing and seeing it clearly, without flinching, without reaching for easy reassurance, but also without unnecessary dread. TON 618 is what it is. It was what it was in the era when that light departed. It may be something else now, something we cannot observe, something the universe has done with those 66 billion solar masses in the 10.4 billion years since the snapshot we see was taken. The universe has been busy. It always is. What we can do is measure what arrived, build better instruments to measure it more precisely, build better theories to explain what the measurements mean. Ask the next question that the measurements make possible. Sit, occasionally, with the unreasonable scale of what the data describes, and let the discomfort of that scale do its work. The universe does not explain itself. It simply continues, indifferently vast, producing extremes that exceed any framework we have built, and then waiting, with unlimited patience, for us to build better ones. TON 618 is the most extreme thing we know of, and knowing it even partially, even through the narrow window of ancient light, is something. That is enough to start with.